Hello everyone, welcome to this last day of the Journées Scientifiques. We're going to start this session with Anaël Hallé about disentangling system of galaxies by comparing optical and molecular IFU data with numerical simulations.
Thanks a lot. And I would like first to thank the organizers for inviting me to speak in this Journée du PNCG. So I'm going to present you some work on disentangling the system of galaxies using different observations and some modelization with some numerical modelization. So the focus of this presentation will be this system. So you have here two images of it. A composite GR I rand on the left from the legacy survey, and more detailed in angular resolution image on the right by the Omega pipeline of the Omega survey and CFHT. So you see that the system is perturbed. It doesn't look like a normal galaxy with no perturbation. You have a dust line. You see the cursor, which appears to be here, and represented in these pictures and other ones in the talks. In the SDSS fiber in the dashed line here. Because, as I'm going to tell you, this system was studied by us because it was identified as a special system in the SDSS survey. So it's a galaxy at redshift roughly 0.1 with a normal stellar mass of 10 to the 11 solar masses and an AC field deduced from ACD fitting, which is about 10 solar masses per year. So it was, as I said, identified as a double peak galaxy in a study by Daniel Mashman in 2020. So he studied all the SDSS survey and identified galaxies for which the spectrum of the SDSS, which is computed in the SDSS fiber here again, was better fitted by two Gaussians than by one single Gaussian. So you have here different emission lines, which are fitted by these two Gaussians in blue and red. And this system looked particularly interesting, and it was also observed with Mwanga, which is an IFU survey. So here you don't have only one fiber, you have fibers everywhere on the sky plane, so you cover the whole system, and you can study in more detail the ionization properties of your system, especially the star formation rate, the kinematics, etc. So, what Barbara Matili-Chiraulo and Daniel Mashman did was to apply the double Gaussian procedure, which was initially used only in the SDSS fiber, everywhere on the Mwanga pixels. So here you have one pixel which is highlighted, and this decomposition of all emission lines, and it was done also in other regions, another pixel here, another one here, and like this, they could identify two different components by very simply saying that when the fitting was better with two Gaussians than one Gaussian, they could say that one Gaussian accounted for one galaxy and the other Gaussian for the other galaxy. It's another simplification, and I'm going to come back to this later. But this is what we did. And with this method, they identified two galaxies, so a large galaxy, visible in gas here. It was also done for stars, and a smaller galaxy, which is superposed on the left side, here in gas and here in stars. So you have on the left the velocities, and on the right the velocity dispersion, which are deduced from the width of the emissions. And they studied the possible configurations of this with the use of the morphology input, this dust line, the shape of the spiral arms. They said that an AGN may be present because of the VLA radio observations and an excitation of the gas which is consistent with the potential AGN. And what we concluded from the kinematic survey was that the ratio between the two galaxies was of the 1 to 9. So the small galaxy, which is represented here in this schematic view, is 9 times lighter than the big galaxy. But the procedure they used is very simple. Attributing one Gaussian to a galaxy can't be completely correct, and we're going to see why. And sorry, I'm a little ill. It was very simple, and studying kinematics from ionized gas is difficult because there is a lot of velocity dispersion. The velocity dispersion of ionized gas is large, which makes a kinematic study complicated. And you have also some subtleties when you do the fitting, because you have to remove from the spectra a stellar continuum, which is not always easy when you have some stellar absorption. And you have also the effect of dust, which is difficult to take into account. So separating these Gaussians is not straightforward. Why? Because double peaks can reduce simply to the rotation of disks. It's nothing new. It's reminiscent of the double horn profiles of H1 disks, etc. So when you have some disk rotation, and when you look at the center of your disk, for example, you have a profile which is not a simple Gaussian, it's a double horn. It depends, the two profiles are computed for two different radii of fibers here. And this profile becomes all the more double-peaked as you expand your galaxy. So you can have double peak just because you have a disk which rotates, and it's of course extremely common. So you have this nature of double peaks which can happen. You have also the effect of bars, which can be to produce a double peak. If you look at a bar, in the direction of the bar, you can have a more double peaked profile than if there is no bar, or if you look at it orthogonally to it. And you can also, of course, if you have two systems with two gas nuclei, have one Gaussian per system and create some double peaks, which was studied in detail in a paper of 2022, where we studied this using simulation database, Journées. And there is also outflows, which Asher will talk about later, which can also produce some double-peaked profile. So, to investigate further the dynamics, the kinematics of this system, we applied for Neuer observations, and Barbara Martelli-Ciralo applied for it and got the data. So this is the molecular gas of this system. So it's in CO 1 to 0. So it traces the mass of the molecular gas, the mass of the dynamics of it. And it's a lot colder than ionized gas, so it traces better the gravitational potential. So here you see on the left the intensity of the CO1 to 0 line with its own contours in gray. In the middle, the velocity, the moment one of the data, and on the right, the velocity dispersion. So as for one guy, you have one spectrum at each location of space, so you can study the kinematics globally. So first, you can combine the ionized data and molecular data to study locally the star formation. So you do this using the molecular gas surface density from the Neuer data, assuming CO2 molecular mass conversion factor, which has a debatable value. You have the star formation rate that you can deduce from the H-alpha emission lines. Here again, it depends on the initial mass function which you use, the attenuation law which you use. So there is some scatter in the values which you can obtain, and combining those two, the surface density of molecular gas and the surface density of star formation rate, you can obtain some Kineckenschmidt diagrams. So you have one as a function of the other one, and you see that there is a correlation in the right parts, which are also the central parts. Here it's color-coded as a function of the distance to the center of the SDSS fiber. And the depletion time, thank you, is a little long. It's about 2 gigayears, while usually it's more for a normal galaxy. It's supposed to be at 1 gigayear. So what we did with the NOIRA data is to try to understand why they looked like they looked. So this is the NOIRA cube, and you see it has an unusual shape. A normal shape would be for a single rotating disk, something like this. So if I go back to the actual data, you have this. So it seems that indeed you have two disks, one which is this part, for this part, and the other one for this one. And so we've been trying to model this data cube with superposing two disks on the line of sight. But as a first simple conclusion from the data, we realized that it was not possible that we had two axisymmetric disks with an axisymmetric conversion factor, because we can't reproduce the whole spectrum of the system, which is the blue line, by just having two simple disks like this. We would miss a lot of observed emission in the center of the velocity region. So we tried the process of having a variable conversion factor, so from molecular mass to CO emission, or the reverse, as a function of the location and per disk, because the emission can vary from different metallicities, from clumpy emission, etc. So we can investigate this, and using this we can indeed reproduce almost the spectrum. So again, it's in blue, and the modeled spectrum is the black dotted line, from the two individual spectra of the galaxies, the modeled galaxies. And we had a configuration like this, with a large galaxy in violet and a smaller galaxy in orange, with inclinations that you can deduce from the shape of the ellipses. And we've been trying to do the same for the ionized gas, doing rectangular cubes of ionized gas emission lines, but for now it's not working perfectly well, so we're investigating what can be happening. So I will conclude by this. So the spectra of galaxies with the red peaks in large parts of the system in the center can indicate some emerging galaxies. And here, for such a system, we've been trying to decompose the system into two disks using both manga data and NOIRA data, which allow, as it is molecular gas, for better dynamical modeling. And the conclusions of this work are going to be submitted very soon, and you'll have all the details, hopefully, in the paper. So, thank you.
Questions for Adele? Very short question.
So, thanks, Anne. I'm wondering, you say that the two systems are merging. So, is there any chance that there is an enhancement of flux due to merger in the star formation or something like that?
Yes, of course, yes. And
is it accounted when you? Like, would that be the thing that changed the conversion factor, or would that happen on top of that?
Well, that's. We can't know, of course, because it's we cannot run truth, but indeed that's what we are investigating clearly, because we think that the larger concentration factors which are necessary to account for this region are due indeed to something happening in the physics of the molecular gas, and this could be due, of course, to the interaction. So yes, that's one of our hypotheses.
I think we're short of time. Maybe I
But
could
the
contribute. You can
depletion
continue.
times are shorter outside, which is a puzzle. The depletion times are shorter outside, which is a puzzle.
They're shorter outside, no. They are outside of what, sorry?
When you show the depletion times on the lower right figure,
Yes.
they were,
They are
at large distances, they were shorter.
No, they are larger. You have here the larger distances.
At large distances, they're at 500 megayears instead of 2 gigayears. So
Yeah,
that,
they are shorter, yeah.
yeah, so that puzzles me because if it was a gas
Yeah, shorter, yeah, sorry.
merge, there would be more inside, I would think. So it'd be very efficient. I don't know.
But the problem with this, I'm not exactly sure to what extent we can trust the H alpha-based SFR, for example, because you have so many hypotheses that that we can't be totally certain that these values are very accurate. You have the extension or attenuation law to consider, etc. So it may not be the ground truth.
Thank you.
Okay, let's thank Annette again. Our next speaker is online. It's Thibault Montard, who will be talking about framing the big picture of massive galaxies, slow quenching since cosmic boom. So I don't know how we...
Thibault, can you hear us?
But also the diversity in terms of environment, because you are looking at a cluster. So obviously, when you look at that, what you may wonder to what you want to understand is how this diversity was produced, and if you have an evolution scheme for galaxies. So it's well known now that you can place galaxies along this so-called Hubble sequence, where on average, red galaxies with no star formation are elliptical, and diski galaxies with star formation are blue. But it's slightly more complicated than that, and especially in the local universe, where we had all the information about their morphology and physical parameters. We could see that you may also have galaxies that have disks, but they are no more star forming. And you also have galaxies that are elliptical and they are star forming. So if you want to understand these mechanisms that basically turn galaxies into red galaxies, you may want to go into the details. So one thing that you can observe in the universe with cosmic time is that the fraction of quiescent galaxies, so passive galaxies where star formation has stopped, is increasing with cosmic time. And at the same time, since cosmic noon, so around redshift 3, what you see is that the cosmic star formation rate is dropping. So those two phenomena, you may want to correlate them or to link them. But the question is, what are the mechanisms that with time have produced more and more quiescent galaxies, and why star formation is less and less present in galaxies with cosmic time? So this is what we call quenching, and this is something I want to discuss. So when you look at the cosmic history of the universe, what you can see is that actually the first quiescent galaxies appeared very early in the history of the universe. So basically, after 1 gigayear of history, you already had the first quiescent galaxies. So this is a very long story. And actually, what you can see is that with at least at low redshift, since cosmic noon, so since the beginning, you had this increase of quiescent of the quiescent galaxy population. You can identify many ways to quench the star formation, and especially depending on the mass regime of the galaxies, you may have different mechanisms that are able to halt star formation in galaxies. So I can identify at least 3 different types of quenching channels. So for example, you may think about galaxies that are quiescent in galaxy clusters, which is satellite quenching if you want, or environmental quenching. You may think of the very early quenching of the most massive galaxies that we are starting to observe with, for example, James Webb. But you may also want to observe the fading, the very slow quenching of massive galaxies, of M-star galaxies typically. And this is the quenching channel I want to discuss today. So this is what I want to discuss today. So typically, if you place your galaxies in either a NUV-RK diagram, so basically rest frame, you will have NUV minus R on one side, R minus K on the other, which is similar to basically drawing the main sequence and the red sequence. So in a stellar mass versus SFR diagram. So what you can identify is the quenching channel that is followed by M-star galaxies. So galaxies that are reaching a mass of M-star, which is 10 to the 10.6 solar masses. So when you basically try to have the whole picture of what characterizes this quenching channel and these galaxies, this is basically what you get. So you can say that, first of all, these galaxies are very massive already, so 10 to the 10.6. So they spend a lot of time on the main sequence. They quench very slowly, so they take basically 1 to 3 gigayears to cross the green valley. So basically the quenching process itself is long and takes about more than 1 gigayear and up to 3 gigayear to happen. So not something violent. Then what you can also associate with these galaxies is the typical size of their dark matter halo, which is about 10 to the 12 solar masses. When you look at their morphology, they preserve their disk. So this is very important to constrain the mechanisms that are at play. And a last thing that has been shown recently is that those galaxies are more likely to experience a merger. But this merger is not the reason for the quenching because it happens after the quenching started, okay? So this happens when these galaxies are already gas poor and in the process of quenching. If you have questions about that, I can come back later on that. So the only way or the only theoretical framework that is able to explain this is something we have to think about the framework of Pichon et al. 2011. In this framework, galaxies form far from cosmic filaments, and once they grow in size and merge and go toward cosmic filaments, they basically start to increase the mass of their dark matter halo, and this eventually may lead to a flip of the dark matter halo they are in, and this is correlated with masses that are in dark matter halo of 10 to the 12 solar masses, and basically M-star galaxies, so galaxies of 10 to the 10.6 solar masses. So just to say that in this framework, the galaxies I am interested in, so M-star galaxies, are predicted to experience mergers along cosmic filaments. So the question is it possible to check whether these galaxies are indeed quenching nearby cosmic filaments? So that would be a strong point to validate this picture and say that, okay, M-star galaxies quenching is happening along cosmic filaments. So this is something we can do. And one survey that happened basically 10 years ago is VIPERS, and VIPERS is a spectroscopic survey, so redshift survey, and you can have the precise distribution of galaxies, between basically redshift 0.5 and redshift 1. So what you can do is reconstruct the cosmic web, which was done here by Nicolas Malavasi with the code disperse. And what you can see is that you can really, even by eye, observe the cosmic filaments in the two Vipers fields. And then what you can do is correlate the distribution of your galaxies, especially with their properties like the star formation rate and their mass. So a second thing that I want to probe in this scenario is that whether galaxies along cosmic filaments experience more or less mergers. But I'm not interested in the mergers of the galaxies, but in the mergers of their dark matter halos. So what I am looking for is galaxy pairs. So this is just briefly to mention how I identify the pairs. And this is based on basically on their radial velocities, obviously, and their separation on the sky. So now when you plot this on the sky, this is what you get. So here what you see is the distribution of your galaxies on the sky. So this is just era versus redshift. So what you see is that you basically see by eye the cosmic filaments and the color codes the distance to the nearest cosmic filaments. So it's consistent. So now if you overplot where I identify pairs of galaxies, they follow basically the cosmic web. And if now you define major pairs, so similarly to how you define galaxy mergers, you identify major pairs with pairs of galaxies with similar masses. So basically one is at least the quarter of the mass of the other, the smallest ones. Okay, so it seems that major pairs are even closer to cosmic filaments. Now, if you look at the properties and basically the plan, so here what you have is the plan, the SSFR versus mass plan, which is a way to identify the main sequence and the red sequence. So at the top, you have the main sequence. And when galaxies leave the main sequence, they start quenching. So between the two dashed lines, what you have is the green valley, where the star formation rate is intermediate, and then you have the red sequence where galaxies are quiescent or passive. And here, what I did was to plot different properties of these galaxies. So typically, on the upper left, you have the distance to the cosmic filament. Upper right, you have the distance normalized by the local density, which is important to disentangle with the effect of the local density, and you really look at the distance to cosmic filaments. And on the bottom, you have the fraction of pairs. And what you can observe is that what is really striking is that basically the fraction of pairs is increasing right at the time when you enter the green valley. And sorry, and the distance of halos also drops. The distance of pairs, so the distance of merging halos is close, it drops towards cosmic filaments. So to conclude, what we have is that it seems that massive galaxy mergers are confirmed to happen more often along cosmic filaments. And second thing, which is very important, is that halo mergers and the quenching of their massive host M-star galaxies appear to be simultaneous. So it seems that those events are correlated and simultaneous. So if I had to put this into a picture for the quenching of M-star galaxies, I would say that you have two galaxies of about M-star that are close to a filament and about to merge. When they merge, basically their two halos merge. When the halos merge, sorry, the fueling in gas is halted and the quenching starts. But the two galaxies are not too much perturbed. Maybe bars can be produced at this time, maybe subtle dynamical effect can be produced, but galaxies preserve their disk. And this is only eventually when they merge that morphology will be affected. So I think I'm about done about my talk. Can you hear me? If you have questions? Yes, so absolutely. So this is exactly why here on the upper right, we have a normalization by the local density, basically. So you normalize by the typical distance between galaxies so that you are not affected too much by the local density. You are really, and also one thing I have to mention, I excluded all the clusters from this analysis. So we are far from clusters, so to avoid to be too much affected by the very high density environment. And at the same time, also we normalize by the local density to avoid this to take this effect into account.
Working since 1 year with Jean-Charles Guyon and Sandrine Codis on Euclid and CFHT observation. The goal of my work is to study the environmental effects on galaxy morphology, and I'm focused on beautiful LSB images from Euclid and CFHT. I'm showing you here the Perseus cluster seen by here CFHT in the air band of megacam, and here this cluster seen by the V's during the Euclid early release observation. And what we can see here is that we have a lot of detail due to the LSB treatment of Jean-Charles. So we see some stream and the intra-cluster light, especially on the V's images here. So you know that a little bit of context. So you know that we have galaxies which are formed close to the filament and evolved from the core of the filament to the nodes, and galaxy lose gas through star formation during this travel. And we know especially that at low redshift we have a competition between the natural evolution of galaxies and the environmental effects. So I'm looking for some large-scale structure effects, such as intrinsic alignment in the filament, but also some local effect due to mergers and stuff like that around each galaxy. So for that, I'm using images from CFHT megacam in the air band of a local filament in order to have a unique data set with some statistics on galaxy morphologies and to see details at low redshift. So on this local filament, I have also zoomed inside a local cluster, which is the Perseus cluster, using the early release observation. So for both, I'm using the LSB pipeline in order to see the details at higher distance of the galaxies. So, for example, I can see the outer part of galaxies, which are more linked to the environment. So that's it for that. And so I will show you a little bit my filament that I study. So this is the Perseus P-cells filament, which is located close to the galactic plane, but in an area without a strong effect of galactic cirrus. As you can see in the background on this map, this is the Planck map of Sirius. You see that this filament is located in an area with less Sirius in blue here. So I have plotted the galaxies in the nearby universe until a redshift of 0.03, and we see this alignment of galaxies with this Perseus filament. And I have images for two regions for CFHT megacam, so the Perseus region and the SR region. So the Perseus region is a region with a lot of Hubble, and especially the Perseus cluster observed by Euclid. And the SR region is more the core of the filament and some void around this filament. So I tried to model the filament using disperse. So I'm trying to see the different skeleton which is observed in 3D in the Perseus filament. So in blue here you have galaxies, and in red the skeleton, and we see in 3D that is not easy to develop the 3D skeleton because we are in the nearby universe where the galaxies are dominated by radial velocity. So we see the finger of God, you can see. But we started with this first result. So with images, I have classified roughly the morphology of galaxies for these galaxies in two regions, so in the Perseus region and in the SR region. So as expected, we observed the morphological segregation. So in the Perseus region, we have more elliptical and lenticular galaxies, and in the SR region, so in the core of the filament, we have more spiral and a little bit lenticular galaxies along the filament. So I have also tracked the local environmental effects. So I'm showing you here some examples, some panels, a tail, some mergers, a shell galaxy here, and in a context of cluster, the ramp pressure stripping on this galaxy. And I'm showing you also the two images here of the famous central elliptical galaxies of Perseus, in order to show you the difference between the CFHT here image and the Viz image, the image with Euclid in color with Viz and NISP pen. So you see some detail, for example, this ring around this galaxy. I have also mapped these local environmental effects in the two regions, and you see that we have a lot of mergers and some tidal effects everywhere in these two regions. And now I will a little bit develop one specific local effect using Euclid early rays observation. So I was in charge with the group on the Perseus cluster to develop the catalog of bright galaxies, and I was after that focused on the disk galaxies, so mainly lenticular galaxies, but also early type spiral galaxies. So I am a sample of 100 galaxies with disk, and I was focused on the outer part of this disk. So I'm looking for some truncation and anti-truncation in the disk profile. So I have extracted the surface brightness profile, and we know that we can fit a simple exponential for a simple disk traditionally, but since 70s we know that it's not the case for every disk profile, and we can classify in 3 types: type 1, type 2, and type 3. So type 1 corresponds to the simple exponential profile for simple disk. Type 2 corresponds to a truncated disk, so after a certain radius we have a lot of planets, which leading to less stars and less gas maybe. So according to the literature, we have 2 main hypotheses to explain this truncation. So the stellar formation threshold, so after a certain radius we come from the stars, so we have a break inside the disk. And the other hypothesis is more the dynamic internal phenomena like bars, which could explain this type of truncation in the surface brightness profile. And we have also the type 3, so this is a non-truncated profile. This is an excessive flux after a certain radius, and is more explained in the literature by gravitational interaction, like small mergers, which produce an excess of stars at a certain radius in the disk component. And I have mapped this type in the Perseus cluster. So what we can see is that we have mainly type 1, so simple exponential disk. But we have also type 3 everywhere in the cluster. So this is the magenta point in this kernel density plot, and we see that these anti-truncation are mainly present at a higher distance from the center of the cluster. And but we see also some anti-truncation close to the center in projection. And for type 2, we have 4 type 2 galaxies. So is not really expected in the center, because we know that some gravitational due to the cluster remove this truncation, and type 2 can become type 1. So, but in this result, we see that we have this type 2 inside the cluster, and we try to model this with different simulation with Frédéric Bourneau. So we use an adaptive mesh refinement called Ramses, and the idea is to have a simple disk in type 1 and see what we can see if we put this type 1 inside an environment of cluster, and we see that we can change the type of surface brightness profile of disk from type 1 to type 2 here. And we know also that the entering orbit can change also the shape of the type. So just to show you that we know that the entering orbit and the stellar formation threshold could explain a bit this variety of type in the core of the cluster. So this is in process, and we will soon publish this. So that's it. And so that's it for early release observation. But I will just to show you some first result on the SR region, so the core of the filament, and we're looking for some spin alignment. So some alignment of the galaxies with the local filament, and this is first result. It's still in progress, so just to show you some stuff. And that's it. So thank you. Oh, sorry. So thank you for your attention, and see you soon for my upcoming publication. Questions for Naomi? One quick question, maybe, because we're still running out of time.
I don't don't know, this is very nice work, and I don't know if it's relevant, but I looked in the TNG50 simulations at the disk profiles of Milky Way mass galaxies, and there was a range between the potential truncated and the anti-truncated in numbers that were roughly equal. Okay, and you find different numbers. So you were looking at clusters. I was looking at Milky Ways being centrals.
Yeah.
Okay, so it's food for thought.
Yeah, okay. It could be interesting to have more statistics maybe for the whole Perseus region. So we look for this type of thing. But I will probably also explore some simulations. So I will explore this.
For whatever they're worth.
Okay. Let's thank Marie again. The next speaker is Quentin Moisson, who will tell us about low redshift groups and clusters of galaxies in the F+ survey.
J'ai Zoom qui crache.
Ah, you don't Zoom.
I was, but it crashed.
If it crashes, just plug in your laptop to the projector. Okay.
Can I hide this?
Sorry, that's me.
No, it's me. I have this. It's okay. Okay. So, hello everyone. I'm Quentin Moison, a second-year PhD student working in IRAP in Toulouse. And today I will show you the first result of my first year of PhD about the study of the low redshift groups and clusters of galaxies in the X-class survey, and more precisely about the redshift identification and the study of the physical properties of the intracluster medium of the galaxy groups. So I'm studying the X-class survey, which is a survey of X-ray detected clusters and groups of galaxies from the XMM Newton archives. So they're detected thanks to the emission of the intracluster medium, which is the hot gas which is emitting in X-ray. Then perform the observation on pointings of 10 and 20 kiloseconds. So it's made it a very deep survey to have very faint clusters. And most of the detections are what we call serendipitous detections, or detections that called by chance. That means that are detections who are not the purpose of the observation, XMM observation. So most of our clusters lie in the outer region of the XMM observations. And at the end, it covers a total of 269 degrees squared, and you have the repetition on the sky on all the classical clusters here. So what makes X-class different from the other survey is that it's mostly composed of very faint clusters, and most of them were also unknown before. And it will also be to have a well-known selection function. So selection function is something like this. It gives you the probability of detection, here in function of the count rate of the X-ray emission and the core radius of the X-ray emission. So it was at the end built to be also complete and homogeneous in the sky for the condition to have a survey who is suitable to perform some cosmological analysis at the end. But the problem is that we don't have measurement for the total mass of those clusters. And this is something that we need to perform some cosmological analysis. So we'll need something that we call a mass observable relation, so relation between the total mass of our clusters and an observable like temperature or luminosity, for example. And for this mass observable, we use what we call the scaling relation of galaxy clusters. But we have a problem, is that those galaxy clusters are not very well known for very low mass galaxy groups, and we have lots of them inside the X-class clusters. So the aim of my study is to study the scaling relation for the low redshift subsample of the X-class clusters, and so also of low mass galaxy groups. And to do so, I perform some temperature, metallicity, mass of gas, and X-ray luminosity measurements of the intracluster medium. And you have here below an example of two scaling relations. And we will focus on the region of the red ellipses, who correspond to the low mass galaxy groups regime. So the first step is to perform some temperature and metallicity measurements, and to do so, we will analyze the X-ray spectra of the intracluster medium. So we have on the left an XMM observation, and we have our cluster who is here. So the first thing that we define two regions. So we have the red circle with the region of extraction of our spectrum, and you have the green ring, so the region of extraction of the background, spectrum of the background. We then perform a fit of the obtained spectra, enlisting only the temperature and metallicity as free parameters, and we can have a measurement of the temperature and metallicity. And to do so, we use the tool named XSpec. But we know that temperature and metallicity aren't homogeneous in a cluster, so the result that we have will depend on the region of extraction that we choose. To fix this problem, we will use a radius R500, but as I said, we don't have the total mass of our clusters, and the radius R500 is determined with the total mass. So I developed a little algorithm to try to approximate this radius using some scaling relations. So we begin with an initial radius, R1. We then measure the temperature inside of this radius, and we then use a temperature radius R500 relation from Lovisari to compute a new radius, R2. We measure the temperature inside of it, and we do it until we converge at 1 arcsecond for the radius. With that, we can have an estimation of the radius R500 and the associated temperature and metallicity. Now that we have the radius, temperature, and metallicity, we can use them to derive the two other quantities we are interested in, who are the mass of the gas and the X-ray luminosity. So we know that the intracluster medium is emitting in X-ray thanks to a Bremsstrahlung effect, and we have that the surface brightness of this emission is proportional to the square of the density of electrons times the Cooling function of the gas, who depends on the temperature and metallicity. Now that we have the temperature and metallicity, we have a direct relation between the electron density and the surface brightness of our cluster. So what we do is that we perform a fit of the 2D surface brightness, and thanks to this relation, in the same time, a fit of the 2D electron density. And at the end, with the surface brightness, we can derive the luminosity, and with the electron density, we can derive the mass of the gas. To perform this fit, we use the MCMC algorithm. So to do MCMC algorithm, we need to have a model that will compare with our observations. So the model that we built is that we take first a uniform temperature with the value found with the X-ray spectral analysis. We take a metallicity profile from Sun et al., who has a higher metallicity at the center of the galactic clusters and the lower at the outskirts. With those two profiles, we have the Cooling function. We take an electron density profile as a beta model with three free parameters. We have the mass of the gas, beta, the outer slope, and the core radius, RC. And we'll also need three background profiles, one per XMM Newton detector, so MOS1, MOS2, and PN. And we'll less them with free value to have an estimation of the local background of our cluster. So now that we have a model, we can perform a MCMC algorithm to determine all the posteriori distribution of all our 6 free parameters. And we can obtain here a corner plot of the results. And to do all of this, we use a Python package named mbpoch2d, who was developed by Jeremy Sanders. So now we have all our methodology to have the temperature, metallicity, mass of gas, and luminosity. So we can perform those measurements on a low redshift subsample of the X-class clusters. So we took all the clusters in the northern hemisphere with a redshift of 0.07 and 0.2. But we had a problem, is that there are some missing redshift in the northern hemisphere, because we had lots of new unknown before galaxy clusters, and what we want is the most complete as possible subsample. So to fix this, to fill this plane, we performed some observation with the spectrograph Mistral at the Observatoire de Provence, and we managed to measure 43 new low redshift clusters, and there are 19 who is going inside of our subsample. And that makes us at the end 115 clusters, with most of them having a confirmed spectroscopic redshift, and for the rest of them, we'll take the existing photometric redshift with a good approximation of the spectroscopic redshift. You have here on the left the distribution of the redshift of our sample, and we can see that it's nearly a flat distribution. So it's a good thing that we cover all our range of redshift to then at the end avoid any biases in our analysis. So here we come to the results. So I managed to have the temperature metallicity for 132 clusters and luminosity and mass of gas for 126 clusters. That makes us a pretty strong sample of clusters at low redshift, temperature, luminosity, and mass of gas. So you have here on the top the histograms of all the 3 measured quantities: the temperature, luminosity, and mass of gas. One thing that we can see is that we cover a pretty large range of temperature, going from 0.6 up to 6 Kev, and that most of our clusters lie below the 2 Kelvin. So we are lots of very cool clusters, and we can also see that we cover a large range of luminosity and have pretty low mass of gas. Most of them are below the 10 to the 13 solar masses. And below you have the error of the measurements in percentage, and we can see that for all our measurements, most of our sample lie below 10% error, so we have really secure and precise measurements. With all of this, we can build what we wanted. The 2 scaling relations that we are interested in are the X-ray luminosity temperature and the mass of the gas temperature scaling relations. So the first thing that we did is that we use a BCS regression algorithm to have a first guess of what our results are, and we compare them with other studies that have been made, especially with the Lobizari, who had a sample that looks like ours. So as they had small galaxy clusters and very big, more massive galaxy clusters, and we can see that we are pretty close. But this needs to be confirmed, because here we don't take into account all the selection effects, so it can be biased. So this needs to model. So we need to model this scaling relation to then confirm our results. And the same for the mass of gas temperature relation. So I'll leave you with my conclusion. And so, as I said, the next step is to do a modeling of our scaling relation to take into account all the selection effects that can happen and avoid any biases in our results. Thank you.
Thank you for your nice work. It's a lot of work.
Yeah.
So have you compared to, for the groups, a lot of work was done by Trevor Pondman in the past. And initially, he found that the LXT relation was dropping for groups with a huge scatter, which is close to what you find, I think. Yeah. You find a drop and you find extra scatter. But later in his career, he said the opposite. He said, well, you really have to go to some fraction of R500. And when you do that, because the groups are so shallow surface density profiles, you have to be very careful that initially they were missing the outer parts. And by including them, for some reason that I don't understand, it went more linear and even maybe in excess compared to the cluster extrapolated relation.
Yeah, I read some studies where they had nearly flat at low temperature. So
he was not doing clusters, he was just doing groups, and he was the best at doing it at the time.
So it means the name?
Pondman, P-O-N-M-A-N.
Okay, I will check out this, yeah. Thank you.
Any questions?
Thanks for this very nice talk. I have a very naive question. I'm not an X-ray expert. So you use a sample between 0.1 and 0.2 in redshift. Why can you not apply your method to higher redshift? Is it just a sensitivity issue?
I can do on higher redshift, but I only focus on low redshift sample to have low mass galaxy groups where we are interested in.
Okay, thank you.
And there's somebody else in the collaboration who is doing the other part at higher redshift. So we split the work.
Okay, let's thank Constantin.
Thanks a lot.
And so the last speaker of the session will be Ashia Shaji, who will tell us about a peculiar group of galaxies falling into Able 2142.
Quentin.
All right, hi everybody, good morning. My name is Asha and I'm a PhD student at Lehma. And today I'm going to present to you my work on a peculiar group of galaxies called Group G, which is falling onto cluster Able 2142. So my talk will be structured in this manner. First, I'll talk to you about why should we study infalling galaxy groups. Secondly, what is so peculiar about this system that I'm studying? And lastly, what are the things that we found by looking at the ionized gas content within this group of galaxies. So firstly, when we talk about infalling galaxy groups, where are they falling into, right? They're falling into galaxy clusters which are one of the highest, largest hierarchical structures of the universe, often found in the cross-section or intersection of cosmic filaments, and they are known to consist of at least 1,000 galaxies with lots and lots of hot X-ray gas permeating its medium. What we know is that clusters grow by accreting galaxies. Recent simulations tell us that 12% of these galaxies that fall into clusters, they don't come alone. They come in groups of galaxies, but they end up accounting for around half of the entire cluster mass eventually. So we know that the environmental effects play a lot of role in morphology, kinematics of the galaxy, but groups are the laboratory where we can see how exactly this is happening. So what really happens to the galaxies that fall into a cluster, multiple things can happen either simultaneously or at different points of their infall. For example, the galaxies in the group can stay bound to the group, or they can get unbound. Their dark matter halo can get disrupted, or they can start merging amongst themselves, or the central black hole can become active, the star formation can increase or decrease, or the shape can just change, their morphology will change. The 300 simulation by Hagar tells us that this is the fraction by which the four top transformations happen, and in most cases, in like 80% of the cases, after the infall, the groups are not bound to the gravity of the group anymore. Or to put it in other words, that if we see a group that's falling onto the cluster and they're bound, the galaxies are bound to each other, they're most probably in their first infall. So the causes of the transformation can either be hydrodynamical effects like ram pressure stripping or gravitational effects like tidal stripping. The only thing we need to note is that ram pressure only strips the gas, whereas the gravitational effects can strip gas, stars, and the dark matter. Now, coming to the system that I'm studying, as I mentioned before, it's group G in Able 2142. The properties of the cluster have been tabulated here. Here we're looking at the optical image of Able 2142 with the X-ray emissions overlaid in purple. So here is the center of Able 2142, and this is the hot X-ray gas that permeates its medium. This is expected. What we don't expect to see is this structure here, and this is the focus. So let's zoom into the structure. It seems like it's a tail, and at the head of the tail, there are a group of galaxies, and the most peculiar thing about this is that this tail is 700 kiloparsec long. And to put it in comparative structure, should I move? Okay. To put it in comparative structure, in comparative context, the only other group that has been observed falling into cluster with X-rays, H-alpha, and molecular gas emissions is this big infalling group in Able 1367, and its X-ray tail is merely just 250 kiloparseconds. And all the jellyfish that we have observed till now, their X-ray tails are less than 100 kiloparsec. So this is the first peculiarity of this group of galaxies. Now, what we are focused on we are focusing on the group of galaxies themselves, especially on these three galaxies here, G3, G4, G5, which has been observed by MANGA, which is an integral field spectroscopy instrument, which just means that at every right ascension and declination, we have a spectra. And just to note that the hexagon is the MANGA field of view, and we see that there are multiple galaxies in this field of view. So past studies on this group of galaxies tell us a couple of things. That one, they're at redshift 0.0935. The star formation rate is quite high, which is around 40 solar masses a year. They have two AGNs confirmed in the X-ray. That is the right one, the right galaxy here, and the central galaxy here is known to be an AGN. What we are claiming is that we're not seeing just three galaxies, we're seeing four galaxies here, especially because there's a color difference in the central one. And this is the center of, we call this A1, A2, B, and C. So B and A1 is the AGN, and they're definitely merging with tidal tails that we can see here and here.
Excuse me. Your cursor is not doing the same thing on your screen and on the main screen.
Oh, I'm sorry. Okay. I'll try to be careful. How do we make this claim is we try, as a preliminary step, we do a single Gaussian fit using n-burst. So we fit both stars and gas at the same time. So looking at the flux emissions in the most prominent gas, like H-alpha, H-beta, N2, we can definitely say that, yes, there is a highly star-forming region in, oh, you're right, in the central white ellipse. And because the O3 is so high, okay, because the O3 flux is super high, we can say that to produce such a forbidden line, there should be some sort of high ionization mechanisms going on. They can either be star formation driven or agent driven, which we can figure out by looking at the flux ratio. So when we look at the H-alpha, H-beta flux, it's also known as the Balmer decrement. We can see that the central part is a dusty star forming region. Looking at the O3 H-beta, it can tell us where exactly is it highly ionized, and it seems as though there is an agent. Yeah, we're confirming the agent in optical, let's say. The agent that we are supposed to see in the middle is probably hidden by dust. And lastly, we also look at the gas velocity and dispersion. Looks like a normal rotating galaxy, but dispersion looks pretty weird, especially in these areas and the edges. And we compare this to stellar velocity, and we we subtract the stellar velocity minus gas velocity and see that the velocity of stars is much higher, especially in these regions. So we use this as a preliminary step to analyze the stars and gas separately because there are multiple galaxies in our field of view. So the first part, the stellar population analysis, is done by a collaborator whose name is Damir Gasimov. And as first step, he tries to recover the line of sight velocity dispersion. This is because the spectra of the observed galaxies is a convolution of the stellar template with a velocity dispersion. So if we solve for this, we get the line of sight velocity dispersion. And if we can get this per bin. And in each bin, if there are multiple peaks in the velocity dispersion, it means that there are multiple spectral components in that one bin or one spaxel. So we use this information to spectrally decompose the 4 galaxies that we have, and we're able to extract the rotation curves for each of the 4 galaxies with its age and metallicity. Now, looking at the gas content of the system, I tried to kinematically model the gas, and we are seeing the same rotating pattern in 3 of the 4 galaxies, that is A1, B, and C. I'm confirming it, but for A2, there's a discrepancy that I'll mention in just a while. We use this kinematical modeling to estimate the ram pressure stripping that's happening within these galaxies. How are we doing it? So the Gunn and Gott criteria tells us that the ram pressure stripping occurs when the pressure due to a pressure exerted by a fluid on a moving body is greater than the restoring gravitational force per unit mass, given by this equation here. So rho is the density of the intracluster medium. V is the velocity at which the galaxy or the group is falling onto the cluster. F is the gas fraction of gas with respect to the disk content, and the sigma 0 is the mass surface density. And RD here is the scale length of the exponential disk that we sort of derive from the kinematical modeling. So to estimate the variables on the left, we use certain approximations. We use the Navarro-Frank-White profile, and we calculate the rho at the distance at which the galaxy group is present. And we also do a crude approximation of the velocity. This is considering, we know that the length of the tail in X-ray is 700 kiloparsec. The age of the tail has been estimated to be greater than 600 megayears. So we simply do a length by age to get the velocity on this plane of sky to get around 1,000 kilometers per second. Now, if we put these equations transpose a little bit, we can get the radius at which the ram pressure stripping starts occurring for each of the galaxies. And this is what we see for each of the galaxies. So the lines with stars is the value for obtained using the stellar analysis. The solid lines are using gas analysis, and the dotted lines, and I forgot to mention that we also consider the orientation of the disk here using the 5 angle. So what we see from this diagram is that A2, which is the galaxy, is the most ram pressure stripped galaxy. And so remember I said that the gas analysis for A2 I wasn't really happy with. That's because of this. So when we look at the stars, if we look at the color bars, it's going from around 50 kilometers per second to 200, whereas the gas is going from minus 300 to minus 200, which is not, that means the velocities of the gas and galaxies are very different from each other, and it really doesn't make sense. So we looked at the spectra to see if we can make sense of what's going on. And what we see is that, so the red is the stacked flux of O3 H beta and O3 5008 and 4960, because these are the only unblended lines in the manga's resolution. And I'm fitting only 2 Gaussians here, but in the residue we can see that there is a 3rd Gaussian for sure. So we are the 2 Gaussians that we are fixing is, one belongs to the velocity of the star of A1, the other belongs to the velocity of star of A2, and finally this broad component here we don't know, but this is still work in progress and we really need to iterate on this. With that, That's the summary. I'll leave you with my summary, and I'll be happy to answer any questions that you might have. Thank you so much for your attention. Questions, Marcia?
In your model, as I far as I understood, you do not take into account tidal forces when you are doing the...
No, we're just simply modeling this rotating circular velocity of stars and gas.
If I understood well at the beginning, you said that tidal forces and tidal stripping are important in dynamics of
It is for sure, yes.
And do you plan to take into account at some point or not?
We do. So the thing is that, because first of all, there are certain, let's say, drawbacks of the study, which is that the manga resolution isn't really helpful in disentangling the different physical processes, because there seem to be multiple physical processes happening within this field of view, and the resolution isn't really favorable to us, but we're trying to make the best of what we have. And so first we try to model the rotating velocities, the rotating gas, and once we hope that once we subtract that from the observed spectra, we'll be able to see other non-circular motions, which can either be outflows or maybe tidal stripping, depending upon the spatial location of the spectrum. Thank you.
Questions? Okay, if not, then let's thank Marcia again.
Thank you so much.
Time for coffee. We come again at 10:45.
Okay, everyone. So welcome back. And to start this session, we have Cédric Dubois from LAM, who's going to talk to us about reconstructing some stellar clocks in a local before.
Sure. So hello everyone, I'm Cédric Dubois from the lab. I'm mainly working on the Concerto project, which is a light intensity mapping. But today I'm here to present a side project that we have with other postdocs from the lab. So it's with Wilfried Mercier, who presented yesterday, Sylvia Martocchia, which is also a postdoc at lab, and Bastien Laville, which is actually working at Thales Alenia Space, and she's more focusing on the off-the-grid methods. So today I will present this work. It's ongoing, so it's only preliminary results that we have for now. But still, I think it's interesting to share it with you. It's about star cluster reconstruction in a local galaxy observed with the James Webb. So you have an example of detection here in this image. So I will first talk about the object, which is here, this one. It's only focusing on this object for this talk. Then I will put some context about the star clusters and to understand why it is interesting to study them. And then I will focus more on the method, which is my main contribution here with Bastien. So I will present you the off-the-grid framework and an algorithm to retrieve the star clusters in this kind of images. And I will show some application, so it's just a first result without any physical conclusion now. But still, it's where we are for now. So this object, it's an ultra-clumpy galaxy. It was observed previously with other instruments than the James Webb. And in this HST image, you can maybe see some clumps, start to see some clumps. And this is after James Webb. So we have 4 bands here. And so I don't know for people in the audience, but you should be able to see really a lot of clumps there. So we want to study this object because we believe it's a rare object, and it was found by Wilfried in the Cosmos Web data. So here I made just a little image with 3 bands, so you can see really the different parts. Some are more red, some are more blue, let's say. About the characterization of this object, so it's local. You have the redshift here. You have the mass, so it's a dwarf galaxy. It's also low surface brightness, and its size is about 600 parsec in radius. What we don't know and we would like to know is, for example, the SFR, the kinematic of this galaxy, its age, the processes of formation, or things like that. So I'm not an expert of this kind of question, but Wilfried and Sylvia are for this project. The main feature of this galaxy is the number of clumps, as you can see. So we want to study them. So I need to put some context about those clumps that I will now call them star clusters. Star cluster because it's like a main category of different clusters. So you have a kind of a review here of what we know about globular cluster, open cluster, and young massive clusters. So the main difference is in the compactness of those objects. So some are really dense and some are really non-dense, less dense. But it's also, there exist some differences in the mass range or in the chemistry, for example, between all those objects. They are quite interesting for the galaxy evolution part also, because you can retrace, or you could retrace some formation of the galaxy based on the interaction of your globular clusters or your star clusters with the environment of the galaxy. They are quite useful because they are really bright and compact, and so you can trace the outer part of your galaxy. And so at the end, we can have some results between the star clusters and the galaxies. So for example, you have a scaling relation between the properties. Here it's an illustration of a color diagram, and you see that you have, for example, a bimodality between blue and red clusters. So we are interested in these kind of things. And if you follow the talk of Timur yesterday, you now know that you have lots of diversity in the population, and you know that it's important to count just the number of globular clusters and star clusters in general. So we are here now, we have this clumpy image. We know that we want to have a precise measurement of the clumps, or star clusters, sorry. But it's hard to do in practice because if you want to do manually, well, it's going to take a lot of time, and if you want to replicate it on other images, then you have to restart again. So we want to do it automatically. Some are blended together, so it's really hard to deblend the clusters between them. And also the image is quite large, so this will take us a lot of effort to compute. So this is what we call an inverse problem. How to retrieve the position in the flux of the star cluster based on an image, an acquisition. So this is well known in the literature, and it's the way we want to resolve it. It's called the off-the-grid framework. This is what I will present now. So you have a pedagogic view of the same problem. So you have some sources here that lies in the continuous space with a different flux. We have three different flux here. Then this is convolved with the PSF of your instrument, and you have also additive noise. And at the end, you have this acquisition, and you want to retrieve the exact position and flux that are here. So this is why it's an inverse problem, because you want to start with the acquisition and get back to the sources. So historically, you might have heard about what we call L1 minimization methods, which are greedy methods, so based on the pixel. This is what we call a grid, is like a pixel grid. Now we have also learning-based method with autoencoders, for example, but all those methods are based on the grid, and we know from this result that you can double the number of estimations, which is quite limiting in practice. So this is why people have developed the off-the-grid framework, which is to get rid of the grid and work in this continuous space. So I will not go into the details, but you have a lot of theoretical branches, which is really useful to trust your result at the end. It was developed in the last 10 years for super resolution macroscopy. So I didn't find any application in astronomy, so this is why I wanted to do it. And its main advantage it's leveraged on the physical knowledge of the observation. Well, what it means in practice, it means that if you know the nature of your sources and the nature of your acquisition, so basically the shape of your PSF, then you are able to retrieve the sources. Okay, so in practice then we have this algorithm which is called the sliding Frank-Wolf algorithm, which allow you to do this reconstruction in practice. So here I put it an example. You have the acquisition, convolved with the PSF, the noisy one, and you have here the reconstruction. So you see that we are able to retrieve the position here of the three dots. And you can do it with more noise. So you have still good results, and even with more noise. And this starts to be interesting, I think, because you see that even in this kind of regime, you are able to retrieve a nice position of your sources. So this is a pedagogical example, but in practice, if you want to apply it on real images, it's become really complicated because it's a really intensive item of computation. So this is where our contributions take into place. So what we want to do is to propose a new implementation, which is called the turbo sliding Frank-Wolf, because it's going faster, and it's based on the neural networks LATS developments. So we had lots of libraries and developments in this area for the neural networks because of the boom of deep learning, and they're actually based on linear algebra and optimization. And it's good because it's what we need to implement the sliding Frank-Wolf actually. So what we want to do is to capitalize on this framework to propose a new implementation of the algorithm. So in practice, we are using JAX. I don't know if maybe people are using it also. It's still ongoing, so we have a first implementation, but we want to do more. So I will present some results that we have with at this stage. So this is one filter of the Galaxy. We are fitting a static profile and removing it. So at the end we get only the clumps, and now I'm working on this image. So I want to identify the clumps. So I cannot do more for now than working on this patch, which is here. So it's 200 pixel by 200 pixel. So we are able to do this result with our implementation, which was not able, we were not able before. So it's a first result. We have 200 clumps detection here, but I'm sure you see that we are missing a lot of them still. And yes, for this result, I need to have an estimation of the PSF. So I'm taking the Gaussian for now, but we know that GWST PSF is not a Gaussian, but still in practice for now, it's working well. So now that we have those detection, we can refit only the amplitude on the 4 bands, and this is what I did here. So it's only on a small patch with 200 detection. So we want to do more to have some to draw some conclusion. But I just wanted to highlight what we can do with that. So for example, here you have the magnitude in the 4 filters, and you have it in black for the Sarsic profile, so the diffuse emission of your galaxy, and all the colors are for one star cluster. So what we see, and you have this average here in magenta. What we see is a different trend between the diffuse emission and the globular cluster. So this has to be confirmed in the following with more data. And here you have the color as a function of the projected distance. We cannot say anything for now, but this is the kind of stuff we want to investigate. And here it's just the color in the overplotted to the image to get an idea. Good stop.
We have time for 1 or 2 slides.
Okay, thank you. So here it's just one last result on multiple detection, on multiple patch. And I just wanted to highlight that we have more than 900 detection. So it's like a lower limit for now in this galaxy. Okay, I will stop with this conclusion. So we have a lower limit on the detection of the club for now. It's too early to draw any conclusion on the physics of the object. And we are working on this implementation of turbo sliding Frank-Wolf. So it's still ongoing. So I hope I will come back with new results. Thank you.
Thank you, Cedric. Gary has a question.
Yes, so after you subtract the Galaxy with the Sarsage profile, have you tried using what 99% people in France use, which is a S-extractor? And how bad is it compared to your method?
Yeah. No, I wanted to do it for this presentation, but I didn't have the time.
Because S-extractor, it will fit a background, a large-scale background to what's left, okay, to the residuals of the surface fit.
Okay.
And then it will look for points, and then you could twiddle it to, you know, you could say, I just want small objects and things like that, and you don't want to move too much, and you can twiddle the input parameters of S-extractor to optimize for this particular problem. And it runs very, very fast.
Yeah, yeah.
And you can do several wavebands at the same time. And
yeah, I really want to do this to compare, because for now I could just make some hypotheses. But our guess is that we will be more able to distinguish between the blended star clusters. So this is why we want to use this kind of method. It is the main advantage compared to Scientifiques, for example. But still, we have to see in practice how it compares.
Can we have a second quick question?
So, not very quick, so when it comes to finding the star cluster, I think that the most annoying step is subtracting the galaxy. So I'm wondering, is it necessary to subtract the galaxy with your method? Is it possible to find a trick or a way that you don't need to subtract the galaxy, just start from what it is? Yeah.
Well, we want to make a conjoint to make the estimation of the Sarsi profile plus the clumps in the same time. It could be better, I think, because when you are fitting the Sarsi profile, you are overestimating because of the clump, for example. And on the other side, when we move it, you can lose some information also. So we want to do it both at the same time, but we don't know for now if it's possible. Well, it is possible, but we don't know if the theoretical guarantees will be not touched, let's say.
Okay, let's thank Cédric again. Next we have Céline Gouin from Paris CFP, who's talking about cluster connectivity.
Okay, so.
Yes,
okay, thank you. So, welcome to give me the opportunity to present my work. So, I'm Céline Gouin at IAP, and my work focused on galaxy cluster and how they are affected by the large-scale environment. And in this talk, more about their gas accretion. Okay. So just a brief reminder of why clusters are important. In fact, they are in the large-scale environment of the cosmic web, so this network of filaments. And at the node of this cosmic web, we have the cluster. So with this infalling region on which filaments connect to cluster, and at the node, the galaxy cluster center. So in this cosmic web, matter flow from void into wall and then via filament into the cluster. So this infalling region around cluster are very powerful regions to probe, in fact, the growth of massive structures in our universe, but also to probe the complex gas physics out of the virial regime inside cluster, and as it was discussed also before, to probe the environmental-driven galaxy evolution on filaments. So here I'm focusing on two distinct points: how cosmic web affects cluster property, and how gas is changing during its infall from filament to cluster. So one powerful quantity to probe cluster and is linked to the cosmic web is the connectivity, so meaning the number of filaments that are connected to cluster, and it has already been proved by this literature and also other paper that connectivity increases with the mass. So the more you are massive, the more you are connected to the cosmic web, and is expected from the hierarchical formation of structures with massive objects are merging, and so it increases the connectivity. But we can ask if it affects also other property of cluster. So for example, we have the dynamical state of cluster that has been probed in the literature. So with dynamical states that we can probe in simulation with their fraction of substructures, their center offset, so the offset between the density peak and the maximum potential, and the virial ratio, so the equilibrium between kinetic and potential energy. And it has been proved in Kushner et al. That the more you are massive, the more you are unrelaxed. So unrelaxed with a large number of substructures, different center, compared to relaxed objects that are rounder, centered, and with low number of substructures. So we can ask if beyond this mass-driven effect, is their cluster property also affected by their connectivity to the cosmic web? So to investigate this, I have used illustrious TNG simulations and construct the skeleton of the cosmic web using T-Rex algorithm. So it's a machine learning technique to detect the skeleton on galaxy distributions and probing again the relaxedness. And what we see is that depending on the connectivity, the relaxedness change. So with high connected clusters that are less relaxed compared to low connected clusters that are more virialized, and it's independent of the mass, so it's a secondary effect. And in fact, we can go up to the mass assembly history of cluster, so considering their mass accretion rate, which is from z equals 0.5 to z equals 0, how much mass they have accreted. So here is the PDF for relaxed and unrelaxed. And we can also probe another proxy of mass assembly history, which is the formation time. So at which time they have captured half of their mass, with the PDF also here. So we can see that, for example, in blue, the unrelaxed halo are formed more recently, and they are in fast accretion phase. So let's focus on these two distinct populations, with unrelaxed objects in blue recently formed and fastly accreting, and on red, the relaxed objects that are early formed and that are slowly accreting at the present time. So if we probe their shape and their connectivity, again, depending of the mass, given it's the first dependence, we can see that in blue, we have unrelaxed objects that are in fact more elliptical and connected to a larger number of filaments independently of the mass. So these objects are expected to be recently formed, highly connected, so they have a large inflow of mass up to the center, which in turn disturbs their shape and so increase the ellipticity. And in contrast, in red, we have more rounder objects with lower ellipticity and less connected to the cosmic web. And so these objects are expecting to have time to relax, given they are early formed, and so with low accretion, and so the center become rounder. So meaning that the large-scale environment, in fact, traduce different evolutionary states of cluster. So we can check on observation. So for now, we don't have a lot of study of connectivity and dynamical states at the same time. But two examples, we have Abel 2142 cluster with a connectivity study by Enasto, which have a big connectivity and which tend to be a recently formed object with an elongated shape, a number of substructures, and its emerging system. And in contrast, we have the Coma cluster, which is more spherical, highly concentrated in the core, so it tends to well fit with prediction of early formed objects. But we need a larger sample of connectivity and dynamical states to really infirm or not confirm this prediction in numerical simulation. So currently, I am a part of one Euclid working package with also Jenny here. So we're working on different key pre-launch paper with one detect the cosmic web with disperse on 2D on the wide survey, but also the connectivity in 3D with spectroscopic data, and just around the cluster led by Florence Arm. So with different observational problems that we have to figure it out, correction of finger of God, projection effect, and so on. And this key paper will be soon on archive. So going to the gas, let's see how gas evolve from large-scale structures to cluster. So here we have the phase space diagram of the gas, so temperature versus density, as depending of different distance to the cluster. And so what we can see is that inside it's hot gas, so the virialized plasma inside cluster as expected. And when we go to the outskirts, it's move up to the WIM, so the diffuse gas, warm, going beyond, with some transition with the WCGM gas, so dense but warm gas, just at the outskirts of the cluster. So it means that these environments are in fact multi-phase. We can also probe the velocity of the gas during this inflowing or outflowing, so compared to cluster. So with the distance depending to the cluster and outflow if the radial velocity is positive and inflow if it's negative. And if we separate depending of the hot gas and the WIM, the two main gas phase, we can see that for hot gas it's accumulating ICM in fact inside the galaxy cluster. But for WIM, we have different regime. Just at the 1 R200, a slow infall with these black things here, but also ejecting WIM with positive velocity. So it means it's inflowing, outflowing around cluster, and at 2 R200 and beyond, it's fast inflowing of WIM gas. So we have multi-flow environment also in and around cluster. And it has been proved from literature that, in fact, this gas is preferentially entering into cluster with following filaments and with some outflowing that going outside filaments. So focusing on these two types of gas, hot gas and WIM, some observation of the most massive low redshift cluster can be observed in X-ray. From Eckert et al., for example, here, with hot gas inside the virial radius and some WIM filaments that tend to appear around. So we decide to separate these two types of gas in simulation and to use decomposition in 2D harmonic space with monopole, dipole, quadrupole, etc. So to see the harmonic excess that we have compared to the circular symmetry, as we already done in dark matter and galaxy, and so with galaxy distribution, and so it tends to highlight filamentary pattern around cluster. So for inside, first, if we consider the asymmetry of the ICM inside cluster, the more asymmetric are in fact the more unrelaxed. There are also the clusters that are the most asymmetric are accreting the most of mass, and they are early form. And in contrast, spherical are with low relaxedness, low accretion, and formed long time ago. So cluster evolutionary states can be probed by the asymmetry of the ICM. Focusing on outside, we can compare the connectivity to the asymmetry, and as expected, so focusing on WIM outside, the more you are asymmetric, the more you are connected to cluster. The more you find connectivity if we just detect the filaments, which is expected given that WIM gas is supposed to follow the cosmic filaments, so it's a good tracer of filamentary structure. So recently, one student that I have co-supervised produced this paper. So, and he also searching postdocs. So if you are interested, he used this technique on the Eckert X-ray observation of the Abel 2744 and use the harmonic decomposition to redetect, in fact, this filamentary pattern using harmonic decomposition, but also using T-Rex, like filament finder on Galaxy, and we find good agreement of the position of the filaments, so using Galaxy and X-ray map. Just to highlight that we now predicting X-ray emission in simulation and find a good matching with new Erosita data and COMA with XMM, but also the soft X-ray emission which is produced by warm gas. And I let you with my conclusion.
Any questions? Okay, maybe I have a very naive question, because unfortunately for me, I only ever care about the stars. So what is the effect of connectivity on the star formation in these kinds of...
Yes, so here I focused on evolution of cluster and gas, but also for the star formation activity, we expect a quenching of galaxies as they enter in filaments before arriving to the cluster. So it's a pre-quenching mechanism that is expected from simulation.
If anyone has a quick question. Otherwise, we can thank Celine again. And now Nicolas Laporte is going to take us to a higher redshift, I guess.
Yes.
A few insights on the first protoclusters.
Is it working? Yeah.
You want a pointer?
Yes, please. Thank you. Yeah, great. Okay, so first of all, I would like to thank the organizer to give me this very nice opportunity to talk here. And just after Céline, we talk about cluster. Now I'm going to talk about protocluster at very high redshift, which means within the first billion years of the universe. I will try to show you that James Webb is great. Everybody knows that. We can get fantastic data with James Webb, but I think we need another instrument and even another telescope. We want to push a bit more the study of this protocluster. So let's start with the main question we have on the first billion year of the universe. Of course, what we're trying to determine is when did the first galaxies and stars form in the early universe, what are their physical properties, and what are their role in the epoch of reionization. And here I'm showing you a simulation where you can see in blue the ionized hydrogen, because when the first star and the first galaxy appear in the early universe, they emit a lot of UV photons, and these UV photons ionize the neutral hydrogen you form after the Big Bang. And the last question, that will be the question I will try to address during this talk, is how did the first galaxies form in the early universe? Were they isolated or were they in group? And to try to do that, first we have to believe people working on simulations. That's what we do when we are observers. And then if we believe simulations, we know that a fraction of galaxies have been formed in overdense region at high redshift. What we know also is that according to simulation, the first protoclusters follow a 3-step evolution. The first one is the inside-out growth, so the size of your protocluster increase, and then you reach a peak of star formation, and then you have the infalling and quenching, when you start to form stars in your protoclusters. But what we don't know is what is the fraction of galaxy formed in overdense region, and we don't know also what is the role played by this first structure, this overdense region, on the reionization process. And here on the plot you can see the evolution of the star formation rate, the total star formation rate, and the fraction of star formation rate in the protocluster core. And we will see on the next slide that the protocluster core is very important, because if we want to cover an entire protocluster at high redshift, for example at redshift 7, the size of a protocluster, we move here, is something, so here you have the redshift and here you have the size of your protocluster, it's very large. If you want to cover the entire size of a protocluster, then at redshift 7, that means something like you need to cover a field of view of 30 arc minutes. So what you can do, however, so of course this is much larger with James Webb or even with other instruments. You can't cover the entire protocluster with just one pointing. You need to do several pointing. However, if you want to focus on the core of this protocluster, in that case you can do it, because the size of a protocluster core at very high redshift is quite small. It's something like 0.2 co-moving megaparsec, which means in terms of radius 0.5 Earth-minute. And then you can do that. And that's why James Webb did that quite very rapidly within the first months after the release of the first data. So here I'm showing you the 3 first deep fields we get with James Webb. SMAX 0723, this was part of the early release observation. Abell 2744, this was part of the GLASS survey, and Goods North as part of the JADE survey. All these data are now public, so feel free to play with that. And in all these 3 images, dataset, we detected protocluster. One at redshift 7.7, another one at redshift 7.9, and maybe one at redshift 10.6. I'm going to describe not all of them. I will focus first on this one, but I will mention the 2 of them, the 2 others at the end of my presentation. So let's go back on this one. The first things you can do when you have images is to select photometrically your candidates. And if you do that, you measure the photometric redshift of all your objects in the field. You take the entire field, which is the entire NIRCam field of view, or you just go very close to 2 objects spectroscopically confirmed, because Hubble observed this SMAX 0723 before, identified 2 bright galaxies. James Webb observed these 2 bright galaxies and spectroscopically confirmed the redshift of those galaxies at exactly the same redshift, 7.66. So if you look in the environment of these 2 spectroscopically confirmed galaxies, this is what you get. You have this excess, let's say, of galaxy between redshift 7 and redshift 8. And what you can do just using photometric data, you can estimate the dark matter halo mass of your cluster, and you can add a constraint here. Of course, this is based on photometry. What we need is to do some spectroscopic confirmation. That's what we get recently with my PhD student, Callum Witten, who will defend his PhD on Friday, so he's not writing any James Webb proposal at this time. This is quite bad for me. So he gets some data, and in May 2024, we've been able to confirm some object in this cluster. So you have 2, 3, 4, 5 plus 2, so that's 6 or 7 galaxies exactly at the same redshift, 7.66, so shift 7.66. But with James Webb, we can mainly spectroscopically confirm the object at very high redshift using the oxygen 3 emission line, oxygen 35007. So we don't have any information about Lyman alpha. And Lyman alpha is quite crucial, especially at very high redshift, because if you can detect Lyman alpha, you know, Lyman alpha is a resonant emission line. So normally, because you are in the epoch of ionization, this line should be absorbed by the neutral hydrogen surrounding your object. But if you have a protocluster, you can imagine that this structure had time to ionize the neutral hydrogen. And then you should be able to detect Lyman alpha in this early structure. Yeah, this was this slide. So here you have an example by Tilby et al. So this was before James Webb with 3 galaxies at nearly the same redshift for which Tilby et al. Detected Lyman alpha. But if we want to do that for this protocluster, so we try to do it with James Webb, unfortunately we didn't get time, so we use the VLT, we use CHEMOS. Here in red you have the near-spec field of view, and here you have, in black, you have the CHEMOS field of view, much larger field of view. So we get 44 hours of CHEMOS time, reaching a 5 sigma sensitivity of 10 to the minus 17. This is very shallow data, but that's the game with CHEMOS. Unfortunately, we didn't detect any Lyman alpha. So 2 hypotheses can explain this absence of Lyman alpha. The first one is that we have a too young structure. This is clearly a protocluster, but it's too young to ionize the neutral hydrogen. Or we have a too low sensitivity. My favorite hypothesis is that we have a too low sensitivity, and we need a new instrument covering a larger field of view, not just this tiny stamp here, but really a larger field of view with a very high sensitivity. And that's why I'm now arguing that we need the ELT. Here I'm showing you a view of the telescope in May 2024. So this telescope would be a 39-meter telescope. I'm sure you all know what the ELT is. The telescope is nearly done at 75%. And its first technical light will be in 2028. Now I'm showing you a view of the inside of the dome, where you can see the mirror. The structure of the mirror is there. We are just now waiting for the 800 segments of the mirror. So this will be done in 2028. That will be the technical light. And then the first light instruments will be there in 2029, and the first generation instruments in 2032. That's the expected date. Let me wait a few minutes because I really like this video where you see the mirror and the size of a car somewhere here, and you can see the size of this fantastic telescope. And now it's my time to make some publicity about the implication of the French community in the ELT. So we are involved in all instruments. The first light instruments, like METIS, Mikado, Harmony, but also on the instrument will be helpful for the adaptive optic. And then we are also involved in the first generation, Mosaic and Endos. So we have imagers, we have spectrograph with very high resolution, up to 1,000, for example, 1,000 for Endos, 20,000 for Mosaic, 80,000 for Harmony. The difference between first light and first generation is just the date when they will arrive at the telescope, between 2028, 2029, 2032 for the first light, after 2032 for the first generation. So my take-home message for the PhD student and the postdoc is that this is exactly the right time. We need you. And that's your time where you should integrate the consortium of all these instruments. You see that many French laboratories are involved in this instrument. So please feel free to join the consortium and let me know that it's much easier to integrate a consortium 6 years before the first light than 1 year before or even at the first light. So try to do that now. So now let me introduce you to Mosaic, because I think Mosaic will be very helpful to continue the study of these protoclusters. But just to give you an idea, Mosaic will have a field of view of 40 square arc minutes, which will be 5 times larger than the James Webb. And the sensitivity of Mosaic, 1 hour 5 sigma, will be 10 to the minus 18 CGS, which is 60 times higher than CHEMOS. With Mosaic, you will be able to use 2 different modes. The multi-objects mode here, where you will be able to observe simultaneously in visible and in the near infrared. And also you will be able to use the IFU, so we will have 8 IFU just working in the near infrared. And with Mosaic, what we will be able to address is all this question there. So how the properties of a galaxy evolve with the distance from the protocluster core, because we will have a larger field of view to explore the entire size of a protocluster. So we will be able to see if the metallicity, for example, evolved as a function of the center of your cluster, how the protocluster influence its environment, or in other words, how the protocluster, how can I say that? Did the protocluster play a role in the reionization, and what the number density of protocluster as a function of redshift. But now let's go back for a minute on these 3 protoclusters, because there is something even more interesting in these 3 protoclusters. If you look at the core of that protocluster, and if you look at the properties of the brightest object in the 3 protoclusters there, well, you conclude that all of them host an AGN. And that's quite interesting. So how we claim we have AGN here, it's because you have nitrogen neon 4, which is a high ionizing potential emission line. And then here, this is because you have a dense, you can conclude from the emission line that you have a dense region. So here, that's GNZ11. That's the object claimed by Roberto Maglino as an AGN. So we have AGN in this one, in Jade, in this one, in SMAX 0723. And there is a rumor claiming that soon on arXiv we will see evidence for AGN in this protocluster as well. So that's quite very nice. It means that if we study a protocluster, we will be able to study the AGN at very high redshift, the faintest galaxy, of course, at high redshift, and also the role for the reionization. And here I'm reaching my conclusion, just to tell you that if we want to observe protocluster, we clearly need to cover a very large field of view, at least larger than what we can do with James Webb. At the center of some protocluster, we have evidence of AGN. And here I mentioned, of course, James Webb, but there is a synergy with Euclid, because Euclid will be able to identify the brightest object at very high redshift, most likely AGN at high redshift, and then we will need to, look in the environment of these very bright Euclid sources at high redshift. And the key question that we will try to address with Mosaic is what is the physical extent of a protocluster at high redshift, and how the physical properties of protocluster members evolve with distance from the core. And that's it. Thank you.
I see Maxime has a question.
Can I offer a counter alternative for the lack of detection of Lyman alpha?
Yeah.
You said that maybe the cluster is too young, but maybe it's too old in a way, that the galaxies are evolved enough that these bright galaxies might have just too much dust for Lyman alpha to escape. Can you...
If I can constrain the dust content in that galaxies?
Like, can you discard this scenario?
I don't think we have any dust constraint from ALMA, but I think we don't have deep data enough to claim the non-detection of dust. We can use the UV slope, and as far as I remember, the UV slope is quite steep. But okay, that's a good point. That's something we should discuss. Yeah.
So another question from Mathieu.
So I have a question about, you're telling that protocluster, basically everything a bit massively in the protocluster just because you have Twitter. But when you say there is AGN, do you have a way to have a comparison sample in the field to say it's more than what is normal for a massive galaxy at that epoch? Or basically they are all in protocluster, so it's become really hard to know what's the role of environment and what's the role of, that's the only place where you have enough baryons to make that.
That's a good point. That's why Euclid, I think, will be important, right? Because Euclid will give you a sample of very massive data high redshift. Then you will need to do the follow-up and to explore the environment, and that would be our sample to compare with. Yeah, that's a good point. Yeah, no. For now, each time we see a very bright object, we look with James Webb, we claim it's an AGN. If we believe the indicator we use to identify AGN at high redshift, correct? Yeah.
We can thank Nicolas.
Thank you.
So next we have Christian Carvajal, he's also from Lyon, and he's going to be talking about stochastic star formation. Richard.
Hello everyone, I'm Christian Carvajal. I'm a first year PhD student at LAM. Today we'll talk about the stochastic star formation history at high redshift. I'm working with the Professor Galaxies and Veronique Bois, and I would like to thank to the organizer for this opportunity to talk. So let's go a bit to high redshift, and I would like to cite Robert Borsanic. One of the reasons to panic because of the result of James Webb we are observing too many galaxies, luminous galaxies at redshift higher than 10. And here, for example, we have a comparison with previous observation at James Webb and the number that now we have in distribution in UV absolute magnitude and also in the spectroscopy redshift. This observation or these results take us to a light evolution of the UV luminosity function that we have here. So the luminosity function just tells us the number density of object per luminosity beam, and here we have a comparison of the James Webb observation with extrapolation based on previous observation. So the first thing that we see is that the data at redshift 9 kind of have a good agreement with the extrapolation. At redshift 11 there is already a small offset, but at redshift 14 this is way more clear. And to see this also, here we have the evolution with the redshift, where we can see that in comparison with the slope of the evolution with the observation and the previous observation and its extrapolation, there is a clear flattening in the slope of its evolution. Okay, but we don't know what this is happening, and there are already some possible driving mechanisms. And here we have some of them. There is maybe an aging contribution, a heavy initial mass function, and a stochastic star formation history, or also maybe an evolution that's attenuation. In this work, we are exploring the stochastic star formation history as a possible solution, but it's important to remark that this is something new that is going on, so it is a highly debated topic, okay? But how we can explain the UV excess with the stochastic star formation history? So, from simulation, of galaxies close to the epoch of the reorganization or in the epoch of the reorganization, have been predict a transition phase of the star formation from being stochastic to continuous. So the gravitational potential is not deep enough to win star supernovas and radioactive feedback, especially in low mass galaxies. And here we can see the star formation rate density, the specific star formation rate, in blue as a function of the time, and in the top the stellar mass. Okay, so we can see that at the beginning we have many bursts of star formation, right? But as the galaxy is forming the stellar mass, we see that the star formation starts to be more continuous, right? So this means that the low mass galaxies are more sensible to a stochastic star formation process. Another important point is the halo mass function, and is a step decline at the brighten of the UV luminosity function. This just means that there are more low mass galaxies than massive galaxies, and these low mass galaxies can go from faint luminosities. More of these galaxies will go from low luminosities to bright luminosities than bright to faint. Okay, so in this way, the stochastic star formation can explain the upscattering of the UV luminosity and the excess at high redshift. Okay, but how we can approach this? So this is a new method, was kind of new, that had been already used, where we try to model the SFH using Gaussian random number generated by the power spectral density. And in this case, we're using a power broken law, where we have three parameters: tau break, that tell us the time scale over which the random number are no longer correlated; the slope, or the PSS, the PS, the high frequency; and sigma, that characterize the variation or the bursting level. Okay, what this means? Here we have this plot where we have the power spectral density in Fourier space. So in this case, this is an example for alpha equal to, for sigma equal to 0.4, and for tau break equal to 100 megayear. That is highlighted here in red. Okay, and after that, we see that the power of the frequency, the high frequency, start to go down. To see this a bit more clear, let's go to the autocorrelation function, where tell us what is the correlation of two events in a time window. Okay, and the thing that we can see is that as we go longer, the correlation goes down, reaching zero time longer than 100 megayears. So, but what is really the variation over the time? That is our SFH. So here we apply an algorithm that do an inverse Fourier transform, and we get this that we have here. Okay, so here we can see the variation with time of the SFH. To see this something a bit more clear, here we have now our real star formation history, and we take as a base model the delayed one in order to compare at different sigmas. Okay, that again tell us about the burstiness of the SFH. So in low sigma, we see that it is clearly smooth and is dominated by the delayed model. But if we go to high sigma, it is dominated by a burst, right? So if we take this and we mock a spectrum of a galaxy at redshift 4, we see that the flux, is higher for high sigma. This is also driving because we have a recent event of star formation rate. Okay, and here we can see that we can cover it in this case with NIRCan from James Webb. So we use this approach, and we also use Siegel in order to try to fit to do some necessity fitting. So what is Siegel? Siegel is a code that models the spectral energy distribution of galaxies to estimate the properties, for example, the stellar mass, the star formation rates, the attenuation. So here we implement the previous approach, and also take into account the age of the galaxy, the seeds for generating the random models. And first, I would like to remark that we did some small tests, and we saw that we can reproduce real color distribution of data with this approach. Okay, so after this, we went ahead for to do the essay fitting on data, and we are using James, that is public data, and it involves a photometric catalog with PhotoC and also with a spacing for some of those galaxies, and we are using for a small sample of around 10,000 galaxies in a range of redshift between 6 and 12. Okay. So how we implement or how we perform the SD fitting? First, it's important to remark that these parameters are really difficult to constrain. Okay, so here we fix alpha and tau break following the literature, and the thing that we want to try is how the burstiness affect the star formation history, the star formation rate, and also the fits. Okay, so for that we did different Siegel runs where we were increasing the sigma that is the burstiness level. So again, on a small sigma, we have a delayed model that is a smooth evolution of the SFH, and a high sigma, we have a bursting. Okay, so to convince you that this chain or affect the properties, here we have a main sequence, if we can talk about a main sequence at high redshift, that's at different redshift beams, okay? So clearly here we see that at low sigma, okay, we form the main sequence, even at high redshift, but at high sigma we have a higher scatter in this relation, okay? So this is clearly show that the main sequence will depend on the SFH model that we use. Okay, but what is the right model for the data? So for this, first we check the distribution of the reduced chi-square, and we kind of see a trend that is kind of minimizing when sigma is equal to 0.8, but it's not too clear, I know, but it's a first hint. So after this, in order to explore a bit more the statistics of this analysis, so we also use the Bayesian indice criteria that allow us to compare different models of the star formation history in order to see which sources present an stochastic star formation history, right? So here I just want to focus in the right part for now, and it's important to remark that we use sigma equal to 0.8 as a base in order to compare the other models. And as we go higher in this parameter, this is telling us that a galaxy have a more significant presence or a stochastic star formation history, okay? So this allows us to do identification of which is the right model for each of the galaxies. Okay, so for galaxies with high delta big, we use sigma equal to 0.8 as the real model, perfect. And in the case of the other galaxies, we use a smooth SFH. So now let's go to see the properties of this galaxy, okay? So the first thing that I want to see is the star formation rate, that we clearly see an increase with the burstiness, okay? That means with the, for the galaxy that present bursty star formation history. And also here we have the final classification. So we have the distribution of the star formation rate in the different redshift beams, and we clearly see that for the galaxies that present an stochastic SFH, we have a higher star formation rate. Now, also it's important to check the distribution of the UV magnitudes. Here we also have a slightly increase, it's not too clear, but when we go to see the distribution in the final sample, so we see also that the galaxies with a stochastic SFH has a higher UV luminosity. Finally, we compute the dispersion in the UV red frame distribution because this is a tracer of the stochastic star formation rate. And we compare with other values in the literature and are here in green, in orange, and in purple, okay? So the first thing is that we see kind of a small decrease, right? So maybe this is due to some selection effects. And also it's important to remark that in comparison with other estimation, this level of burstiness is not enough to account the excess of UV emission seen from the UV luminosity function. Finally, I will leave you with the conclusion because I think that the time is over.
Christian, so any questions? Mathieu?
Yeah, Christian? Nice talk. If you have fundamentally for making your analysis, you need to see something in UV, I guess. So as you say, there is a big selection bias towards what they are in the burst phase because you have more young stars. And how do you think it's possible to correct for that? Because it's really cool to know they are bursty, but fundamentally you would like to study the entire population. So is there a trick to go back to the more clean selection, which is not biased?
Yes. Other thing that we can do is try to do this analysis also in lower redshift galaxies where we have maybe a more complete sample. But also it's important to remark that we will think that maybe at higher redshift the mass of our galaxies are smaller, right? But for example here, the thing that we see also is that maybe we are not complete also at high redshift, right? So there is something else that we have also to take into account because like at high redshift it will be more difficult to see low mass galaxies, and also here we are not complete. So maybe to do a more fair analysis also we have to check the low redshift galaxies, the lower redshift galaxies.
Okay, so another. But okay, it's very good.
Thanks for a nice talk.
Thank you.
Maybe you showed it, but I missed it.
Have you tried taking mock observed spectra from simulations where you know exactly the star formation history and see if you can retrieve that with SIGA?
This is like the next step because we want to check what we can learn from the spectrum because, as you said, in the spectrum maybe we can see more recent star formation because there were some work before that they were comparing what you can obtain from the spectrum and also from the photometry instead of the star formation history. So this is something that we want to check. Thank you.
One last question from Joanne.
So you apply this to very high redshift data, James Webb. Have you tried to low redshift universe?
Not yet, but yes, this is something that.
There's much more data, right?
Yes. Yes, because here we go from 6 to 12, and we have like 10,000. Of course, we do some selection, but if we go lower, we have like I don't know, maybe 40,000, something like that.
Okay, let's thank Christian for this time. And next we have Maximilien Franco, who I think is still in Texas, technically. Right?
Yeah.
And he's going to talk to us a bit more about these high redshift galaxies.
I didn't admit you yet? No.
Okay, so thanks a lot for having me here. I'm Maximilien Franco, postdoc at the University of Texas. I will move soon in Paris, well, next week in Paris. And during this talk, I will present the Cosmos Webb survey, the observation of the cosmos field with the James Webb Space Telescope. We will soon release the images, the catalogs of the survey, and I will highlight some of the results we have about the epoch of reionization. The reionization of the intergalactic medium is a relatively fast process. We know that it stops at redshift around 6, with a midpoint at redshift 7.7, but it's still difficult to have a big picture of it, especially toward the beginning of the reionization, and to know exactly what are the main drivers of the reionization, if it's the low-mass galaxies, the high-mass galaxies. And before the launch of the James Webb Space Telescope, we were limited to just a few numbers of galaxies at redshift greater than 8. And with already a lot of questions about the shape of the UV luminosity function, with already a discrepancy that started to appear between the expected number of galaxies, the black solid line here, and the observations here. A lot of questions also about the evolution of the UV luminosity function at redshift greater than 8, with some studies showing a slowdown of the evolution of the UV luminosity function at this redshift. And a lot of questions about the evolutions of the stellar mass density to understand if the stellar mass density is still proportional to the mass densities of dark matter halos at very high redshift. And if we were limited to these galaxies up to redshift 9 or 10 before the launch of the James Webb Space Telescope, it was mainly due to the filters of the HST able to detect the Lyman break up to redshift 9 or 10. And it's the reason why during the past 6 years, during 2016-2022, the most distant galaxies remain at redshift 10.6. Since this barrier I have been overcome with a lot of observations, tens and tens of observations of galaxies at redshifts greater than 10, and some spectroscopic observations of galaxies up to redshift 14.2. Like last week on Archive, we had like the spectroscopic confirmation of this galaxy with O3 detection at and giving these galaxies a redshift 14.18. I will make a small parenthesis here. It's a huge caveat on the search of distant galaxies. all these galaxies like that with a break at 1 or 2 microns are not all distant galaxies. The most famous example is probably this galaxy with a huge break at 2 microns with very blue colors. All the SED fitting codes will attribute to this galaxy a very high redshift. But this break can also come from a large amount of dust here that will absorb the light from the stars and re-emit in the infrared. It's what we call the optically dark galaxies. We detect some of these galaxies with the good ALMA survey, with Mathieu Battermin, with Benjamin Mignelli, with David Elbaz. We have absolutely nothing up to 2 microns and a galaxy very bright here. And now, with the James Webb, it's absolutely incredible to see how these galaxies appear very well in infrared. And if all the SED fitting code give also to this galaxy a very high redshift, is because of the apparent blue colors due to strong emission lines that artificially boost the flux in some filters. I'm closing the parenthesis here. I'm coming back to this galaxy. This galaxy is absolutely incredible in a lot of points because of the redshift, because of the size of the galaxy, because of the absence of emission lines. So probably the light is triggered by star formation in this galaxy. And because this galaxy is absolutely it's incredibly luminous, with a UV luminosity of approximately -21, and this galaxy has been detected in a small volume. One of the questions now is to understand if these galaxies are rare in the universe or not, and how we can link this galaxy to the environment. And to do that, the only way to explore this is to observe a large part of the sky, and it's really the idea behind Cosmos Webb, to observe a large part of the sky and to cover the patchiness of the reionization. On this simulation, which show a slice of the universe at redshift 7 and at redshift 9, we can see the pink patches, it's the distribution of the ionized hydrogen, the blue patches are the neutral intergalactic medium, and if we limit ourselves to small region of the sky, the red square as the size of the Hubble Deep Field, we can easily be only on a neutral region, on an ionized region, on a peak of density, or in a lack of density. So with Cosmos Webb, we really want to encompass this variation, to encompass the size of a reionization bubble at redshift greater than 9. To give you another idea of the size of Cosmos Webb, I did this small video showing the size of the Hubble Deep Field and a D-zoom in Cosmos Webb. And we can see in this image approximately 1 million of galaxies. Well, and few stars. Yeah, a few stars.
So how wide? 1 degree?
0.6.44. During the first 2 years of the James Webb observations, a lot of effort has been done to observe extragalactic fields with different strategies, some very deep observations. It's the case, for example, for SEERS, for NGDeep, to observe some gravitational fields, and all these observations will give us information on the faint end of the UV luminosity function. With Cosmos Webb, we really have the possibility to explore the bright end of the UV luminosity function. And these very deep observations give us a lot of information on the faint end. For example, reveal the exceptionally high ionizing production rate of very faint galaxies. The Cosmos Webb survey has been observed in 3 parts. It's 0.54 square degrees with NIRCam in a contiguous way, 0.18 square degrees with MIRI. And I will first present the first part of this survey and give then some information about the other parts. On the first part of the survey, the first 4% of the survey, we detected 15 galaxy candidates at redshift greater than 9. We can see the spatial distribution on the left, the SED on the right. For the moment, it's still candidates, galaxies at redshift greater than 9. We are waiting to have some spectroscopic confirmation for these candidates. and we explore the evolution of the UV luminosity function with the redshift. Because we are shallower than other surveys, we are biased toward the brightest system. To give you a comparison, GNZ 11 is just here. We are among the brightest galaxies at redshift between 9 and 11. We study the evolution of the beta slope as a function of the UV magnitude. So globally, we are consistent with results from simulations in green here. We are a little bit below the result from the literature, from the UltraVista survey, but these galaxies are have a redshift a little bit below and are really, really massive. And there is a correlation between the stellar mass and the beta slope. Between the redshift and the beta slope, redshift greater than 7 at a given stellar mass, this relation is relatively constant, it's relatively flat. And to be sure to have no bias on the evolution of the beta slope, we have to be careful because some SED fitting curves are limited in some templates and cannot explore like this part of the beta slope. Concerning the beta slope, we didn't find any values below minus 2.6, any extreme values. It seems to show that 500 million years after the Big Bang, the universe is already a little bit enriched in metal. We also study the evolution of size of these galaxies. These galaxies are very compact with a radius between 200 and 600 parsec. These results are relatively consistent with the results from other surveys with Sears or with glass, for example, with a correlation between the size and the magnitude. And this correlation here has been seen in all other surveys. These galaxies, now on the full part of the survey, some of them are really, really luminous, with some luminosity greater than or equal to the luminosity of GNZ 11. We derive the stellar mass of these galaxies, so it's not trivial at all to derive the stellar mass at redshift greater than 10, but if the redshift and the stellar mass of these galaxies are confirmed, the star formation efficiency, so the fraction of baryons that have been converted into stars over the lifetime of the galaxies, is relatively high, reaching 0.03 at redshift 10 and even 0.5 at redshift of 12, leaving just a few room for other components of the galaxies. So the stellar mass is probably not the most robust indicator of these galaxies. In a lot of cases, the stellar mass has been derived for the little red dots, and we have shown that the little red dots, the SCD of these galaxies, have a very typical V shape, like that, and this SCD, depending of here the emission is due to an AGN or a stellar emission, can be overestimate the galaxies by the stellar mass of the galaxies by a factor of 1000. It's not the case of these galaxies. These galaxies are clearly resolved. We can see them here. We derive, thanks to these very bright galaxies, the UV luminosity function. We can see a good agreement between different surveys, between NGDeep, between Sears and Cosmos Web. We observe a slow evolution of this UV luminosity function between redshift 9 and redshift 12, and we are much higher than results pre-James Webb. It's very well illustrated by Steve Finkelstein, by this plot. It's interesting to see that this excess of galaxies is detected only for the brightest system. For the faintest galaxies, we don't find this excess. We have different possible explanations for this excess. I don't have time to go in details on these different observations, but we're trying to investigate these different possibilities with Cosmos Web. Thank you for your attention, and I leave you with my conclusions.
Thank you, Maximilian. Do you have any questions from the audience? Okay, Nicolas, at the back, yeah.
About the star formation efficiency, you say that it's a bit high, but I think in Labé et al. It was even more, it was higher, right?
Yeah, in the paper from Labé et al., well, he had some star formation efficiency greater than 1, that it's currently impossible on a lambda CDM paradigm. But what I wanted to show is in Labé et al., it was really some little red dots. It was galaxies extremely compact, and if we think then the majority of the part of the emission at 1 or 2 microns is due to an AGN, we can totally overestimate the stellar mass. For the little red dots, the stellar mass is much more uncertain than this kind of galaxy. But when we speak of stellar mass at redshift 10, it's also like something very, very suspicious. In a lot of reasons, we don't know the evolution of the mass-light ratio at high redshift, if there is an evolution of the IMF, if there is an evolution of a lot of things, it's totally uncertain. But in if we think, and it's probably not the case, like the IMF is constant between redshift 0 and redshift 10, we get this result.
Okay. There are no other questions. Then I suggest we thank Maximilien again. And we break for lunch.
Yes, good afternoon. We will first of all hear Maxime Fabiche, which will work on the modeling dust assembly in the early galaxy.
Okay, thank you very much. Thank you for having me here. Sorry for not having been here the past 2 days. I was caught up on teaching. I'm now a staff member at l'ERMA, working at Sorbonne University. And today I'm going to talk about some of the work I've been doing in the past few years using a simulation that I ran a few more years ago. Can everyone, am I loud enough for people in the back? Good. Okay, so the main, I guess, starting point for what I've been doing is the result, the puzzling fact that JWST is painting a very different picture of high redshift galaxies than what we've had before. Max told us about the very bright galaxies that we have now detected routinely in all of the fields. But something else that is relatively new is that we detect, compared to what we had before JWST, many more dusty galaxies. Before the 2020s, before JWST, we had very few high redshift galaxies that were full of dust. But now, JWST has revealed 2 kinds of galaxies, at the highest redshift that we know. Well, maybe not redshift 14, but let's say redshift 7, 8, which is already high redshift, still high redshift. So we had, on the one hand, galaxies that seem extremely dust-free, with extremely blue beta slopes that we detect out to very high redshifts. And at the same time, as Max hinted with the HST dark galaxies, we are now detecting galaxies that are apparently full of dust, or at least very obscure and very rare. And this is something that's important if you're studying dust, but it's also something that's important if you're interested in the galaxies themselves, because I think Max showed this galaxy, which was mistaken for a redshift 17 galaxy when it was actually a redshift 4.9, just because it was a dusty galaxy with strong emission lines. So understanding the fact that we can have strong emission lines and dusty galaxies kind of tells us that we need to understand a bit better how these bright galaxies grow, evolve, and how the dust content assemble, how it's distributed in them, and that kind of thing. So for that, what we really need, beyond more data, is detailed galaxy models that can capture the physical processes describing how dust grows and forms in the ASM, and how it's distributed spatially in the galaxies, and how we can use this simulation to compare them on the observational side with real data. And so for this, I've been using one such high-resolution simulation that I've been developing with a relatively large team over the past few years. And this is the obelisk simulation, which focuses on an overdense region of the universe, not quite a protocluster, but the environment around a protocluster that will collapse into one of the most massive clusters at redshift 0. And one specificity of this simulation is that by focusing on such region, we can keep a high resolution in the simulation. We can model various processes that we're interested in at high resolution. For instance, star formation, supernova feedback, but also black hole growth. And for what will matter for this talk, we can model dust while keeping a resolution of about 35 parsec, which means that we can start to really resolve the ISM of these galaxies, even though we have massive galaxies, which typically requires a large volume. When I say high resolution, what I mean is that we can zoom in the galaxies and start to resolve features in the disks, maybe spiral arms, maybe tentatively bars in some galaxies, as I'll show later. But we can really resolve what's going on in these galaxies, and that's important if you want to describe the spatial distribution between stars, gas, and dust. Digging a tiny bit deeper, the way we are modeling dust in the simulation is, let's say, a simplified model to the simplified version of the model that Johan presented yesterday, I think, where we go one step beyond the usual way of modeling dust in simulation, which is by assuming a constant dust-to-metal ratio. What we do here is we follow the global dust mass in each part of the galaxy, or the global dust density, if you want. And for this, we model the growth by, the apparition of dust by injection through supernovae, typically, and the growth of dust by accretion of metals. And we also model the dust destruction through two main processes, which are destruction in supernovae shock, that we try to resolve as best as we can in the simulation, and thermal sputtering, meaning that dust is going to be destroyed in hot gas. And when we do this, we can, as I was saying, describe spatially where the dust is in the galaxy. So here I'm showing one relatively massive galaxy at redshift 7. And this is the gas distribution where the stars are, where the young stars are, so star formation rate, surface density, and here it's the dust surface density. And we can see that dust is kind of in between the gas distribution and the young star distribution. Maybe a bit more quantitatively, a way to see where the dust forms and appears and exists in this galaxy is through this phase diagram that shows as a function of temperature and density, again for the same galaxy as I was showing before, the total gas distribution, and we can see that so white means more and dark means less gas, and we can see that the bulk of the gas distribution is relatively warmish gas in the halo. We have gas that cools down to low temperature, down to 100K-ish, which is where we will become stars in the simulation. But we also have hot gas that's entrained in outflows. And focusing on the middle panel now, we can look at where the dust is, and this is showing the dust-to-gas ratio. And we can see that in the dense gas where the stars are forming and when the supernova are exploding, this is where we are injecting dust, and this is where we're finding most of the dust. We also have some dust in the outflow, and this is likely dust that is entrained and not quite destroyed yet. And the way I know this is because this is also metal-enriched gas. So this is dust-to-metal ratio. So these are regions where there is more dust than the average, and more dust, than the average in the outflow, and comparable to what we have in the ASM. And more specifically, in this kind of diagram, we can follow where dust is formed and destroyed, and we can essentially, this is what I'm showing here, where the red area is showing how fast dust is formed, and blue is showing how fast dust is destroyed. And we can see that in dense gas, in the ASM where we form stars, this is also where dust is going to grow the most efficiently, while in the outflows, in the hot dense outflow, this is where dust is going to be destroyed predominantly. And this is, we think, a telltale sign of the fact that there is dust growth in the ISM just there. Okay, so now that the model is kind of in place, we can use this to try to understand what are the properties, what kind of properties I predict for the galaxies from this kind of simulation. keeping in mind that this is going to be a slightly biased environment, but at the same time, it's likely that most massive galaxies are in overdense environment because they are the overdensity level. So the first thing we want to look at is just the dust mass as a function of stellar mass, and I'm showing here what's happening at redshift 7, I think, color-coded by a star formation rate. And it's very expected that the more massive galaxies are also the more star-forming one, where most of the dust is going to be produced as well. And so they're going to be more massive, more dusty, and more star-forming. And it seems to align fairly well in terms, more quantitatively, it aligns fairly well with that other models that I'm listing here are predicting for this kind of redshifts. Also fairly expected is the fact that now I'm comparing at different redshift the same kind of curve. So the solid lines are the median of these trends. And as a function of redshift, going to lower redshift, going from yellow to or purplish, we can find that at fixed galaxy mass, over time galaxies get more and more dusty, which is what we expect from dust enrichment in these galaxies. The positive thing that maybe I wasn't expecting that much when I started is that it actually matches observation relatively well without having been baked in. In particular, so we are slightly above what the alpine galaxies are finding in orange here, but we are a very good match for the Rebels galaxies at redshift 7, which are bright, dusty galaxies, bright galaxies that happens to be fairly dusty. Now one question is, now that I've told you that these galaxies get more and more dusty, is this driven by dust growth, or is this driven by metal enrichment and just constant dust to metal ratio? And what I'm showing here is the mass metallicity relation for galaxies at different redshifts, still color-coded the same way. And we can see that this time, as a function of time, or redshift, it seems that, okay, 2 minutes? Yeah. Okay, so it seems that the amount of metals decreases, but the way we interpret this is that this is an artifact of the increasing dust to metal ratio over time. So we have more and more dust across the mass range, and if you only account for the dust in the metals, or the metals in the gas phase, this is going to decrease slightly with redshifts. Okay, now the question is, from this, what can we actually observe? And what does that tell us about real galaxies? So for this, I'm essentially post-processing the simulation that I have with a radiative transfer code. And if I don't account for dust, I get a very bright image. This is what I was mentioning earlier, saying we can have hints of bars. When I then follow the gas and dust radiative transfer, I find something where we can see dust lanes. We can still see hints of maybe bars or weird features. Unfortunately, when you convolve that with an observational PSF, the best you can hope, I think, at this kind of resolution is some form of color gradient in the galaxy, which is already kind of nice at redshift 7, to be fair. Yeah, so maybe one result that I'm puzzled about and that I kind of like is that one approximation that we have to do when we are doing this radiative transfer is we have to assume some dust extinction law. So essentially, when the photons are going through the gas and the dust, we have to assume that as a function of wavelength, how it's going to be absorbed and reflected on dust grains. And from this, we can get, in principle, the attenuation law, but we can't predict directly the extinction law. So I have to assume 2 different extinction laws. And I'm here comparing what I get for the relation between the UV beta slope versus UV luminosity for these 2 different extinction curves, taking 2 extremes, one that is SMC-like and one that is Milky Way-like. And what I find is that, well, first, I don't get extremely blue galaxies, but this might be just because I've a little too much dust, maybe. However, I find that there is a strong difference just based on what's the intrinsic extinction. It seems that the Milky Way extinction law gives me a slightly better match for the beta MUV relation. Unfortunately, then, when I do the same exercise and looking at the IRX beta, which tells essentially how blue the galaxy is versus how much is absorbed and so re-emitted in the infrared, I get the opposite, which is that I assume the SMC law, the dust extinction, I get an apparently better match with the data. And what that tells me is that there might be spatial offsets between gas and dust, and I can discuss that a bit more in detail. But yeah. And I think in the interest of time, I will stop here and leave you with my conclusions. Thank you very much.
And actually, thanks a lot. It gives lots of sense to what we are now seeing with the data, and we see indeed some redisplacement between the blue side of Journées seeing one block and the red one seeing another one. And my question is, like you show that also in the simulation, that you can see how it evolves temporarily, that you can see. Is the dust moving, or is it remixing, or it's more stay two regions which cannot really live their life for a little while?
I haven't looked at the evolution of a single galaxy over time. My expectation is that dust, in the ASM, dust would mostly follow the cold gas, and it will be ejected slightly, but the region will, star-forming region might clear out their local environment, and there are probably some subtle timing things that happen that lead to these offsets, I think.
Okay. Another question? Yeah.
So, thank you for this presentation. In one of your galaxy images, you said you had a bar.
I mean, what I'm really saying is that if you squint really hard, you can see here that something might be slightly elongated.
What?
There is no kinematic information that I've looked at all.
No, but still, what redshift are you?
This is redshift 7.
7. Okay.
But again, I'm not saying you would see it, and I'm not saying it's really what you would call a bar if you were doing kinematical analysis. I'm saying there is non-axisymmetric feature in this picture.
Right now with JWST, we only see these set of features.
Yeah, but this is the resolution, this is an optimistic approximation of what you would see with JWST because I didn't even pixelate it.
Okay.
Okay. So I suggest we take again Matthew. And now we will have two presentations on the cosmic line 3 simulation. And first of all, the work of Joe Lewis working on the Lyman alpha forest and correlation with galaxies.
Thanks. Hi everyone. So I'm Joe Lewis. I'm a postdoc at IUP at the moment. And today I want to talk about a project that's a continuation of my work during my PhD. And it's going to rely on the Cosmic Dawn 3 simulations that I'll talk about now. And Claire will also say a few words about afterwards. So I have this very generic slide about reionization, but we've already had Max Siemens and other people talk about it. But I do want to spend a moment talking about this very pretty picture that Pierre made of the previous simulations. It is very illustrative of why we try and make these large and difficult to produce simulations, okay? And it's actually a light cone. So this axis here, the x-axis, is a time dimension, okay? And this one is a normal, the y-axis is a regular spatial dimension. And so going from right to left, you're coming from the beginning of the simulation early in the universe, okay? And you see that these grayscale colors are showing you the underlying density throughout the simulation, and these blue splotches that start to emerge a few 100 million years after the Big Bang. They are the first ionizing bubbles that appear in the simulation, and that's being driven by the first star formation in the highest density peaks. Okay? And you can see, as you go on, the bubbles get more and more numerous, but also the bubbles are individually growing, and eventually you reach some form of complete reionization. But what I think is really cool about this image is if you take a single column of pixels, so here, and you go up and down, you see that the local outcome is very different at a given time. Okay, so this is illustrating why it's important to run these large, expensive boxes, because you really want to capture all the different outcomes that depend on the local galaxy population and all the complex physics that goes into producing these photons. And so I just have this almost boastful slide that's kind of an advertisement for Cosmic Dawn 3, but also a disclaimer about why there aren't that many of these simulations. So Cosmic Dawn 3 is the latest of 3 simulations, and it's the largest that Pierre and I and other people have been running. It has a huge grid, okay, an unreasonable number of resolution elements, okay, so 8,000 to the cube per field, okay, and for the dark matter, okay. And that lets us, even though we have a uniform grid across 100 co-moving megaparsecs, we still are able to have a sort of decent resolution to resolve star-forming galaxies, but also a very good resolution in the IGM, because we have at least two physical kiloparsecs everywhere. Okay, and Pierre managed to get this to run all the way down to Redshift 4.6 of this huge machine called Summit in the US. And it took an unreasonable amount of CPUs and GPUs, okay? But I just want to insist on the size of the simulation. Okay, so when we are running these simulations, the curves that we look at whilst it's running, and then afterwards, are things like this, okay? So I'm just going to focus on this in this presentation on the left. And it shows you the average neutral fraction as a function of redshift. So starting early on this simulation here, it's 100%, everything's neutral in the IGN. Okay, and then we saw the first stars start forming early on, and the curve starts to go down. This is the blue one, okay, that's code 3. And you can see there's this weird locus of points here and there, which are constraints inferred from observations, okay? And you see we do pretty well with respect to these constraints. At least we do much better than the previous simulation, Coda 2, which is in orange here, you can see. It's a lot of work getting that to work properly. Okay, but the problem with these kinds of constraints, when you're looking at the realism of the realization in the box, is that they do depend quite heavily on modeling and in sometimes even other simulations, okay? So they're not direct comparison to the observations. And if you want to do that, you have to do things like this, which is create full mocks of the Lyman alpha forest in the simulation, okay? And so this is an example for one line of sight on the left, where you see the different physical components taken from the simulation gas. And at the bottom, there's the resulting normalized Lyman alpha flux that you're getting through a column of 8,192 pixels, or cells, okay? And you can see this is at redshift 5.4, so its realization is basically over in the box, or almost in many places. And still you can see that there are large patches where there's very little transmission through this particular line of sight. And then if you want to get fancy, you can try and make some visualizations with many of these lines of sight. So I have like 1,000 per snapshot, so I have a few 10,000 lines of sight to do things like this. And I've ordered them by their transmission, okay? And so at the top you have 1% of Lyman alpha photons going through the box. And at the bottom you have 60%, okay? And then you have the redshift evolution here. And then what you can do is you can make, for each of these lines of sight, you can make an effective, or you can produce an effective number of the transmission, okay? And then you can, for a box, you can follow the evolution of the transmission in all of these lines of sight. So this is what you see on the left here, okay? And so this is early times, this is late times, okay? And Cosmic Dawn 3 is the blue curve, as before. And this is a collection of constraints from observations. Some of them are a bit old now, okay? But you see that overall we do a pretty good job, okay? On the right is a different way of looking at things. You just take away the exponential by putting in a logarithm, and you get the optical depth instead of the transmission. So the weighting is a bit different. But having the two together shows you that things could be better, right? Okay. You see that at early times, if you look at the optical depth curve, we're a bit too opaque. And then if you look at the flux curve, you can see that at late times, maybe we're a bit too transmissive. So these comparisons are still not perfect. We don't have quasars in the simulations from which to launch these lines of sight like observers do. But I think these are maybe symptomatic of the comparisons that we're always doing for these simulations. So we treat the galaxy and the IGM data separately, okay? So we'll be looking at the Lyman alpha forest and comparing it to our calibration simulations, and at the same time we'll be looking at some galaxy statistics like the UVLF, okay? And so if you change a bit the dust model, we can maybe make your galaxies fit and say everything works well. And I think what's exciting is we're getting new data sets that combine this information in one kind of constraining package. And so that's what I want to talk to you about today. So the correlation between the galaxy population and the Lyman alpha forest, okay? And so this is a paper from last year. And you see 4 lines of sight, okay, of fields of Lyman alpha emitters or galaxies. And each line of sight has an associated flux in the Lyman alpha forest, okay? And then the density map is just the density of Lyman alpha emitters or galaxies, okay? If you look at them, they have very different transmissions through the central line of sight, but it's actually hard to tell them apart, okay? This is the least transmissive, okay? But it's not obvious, right? You have much larger density peaks of galaxies around here. So one of the fun things I wanted to look at is if you have a crazy simulation, sampling of this kind of field. If you take your simulation and you run thousands of Lyman alpha skewers in the same direction, and then you look at your cube face on, what do you see? So this is redshift 6 in Coda 3, and on the left is the Lyman alpha optical depth, and on the right is the stellar mass. And so you can see actually pretty clearly by eye, you can do this correlation, where you see this region here, which is slightly higher transmission than the black region, that is where there's the most stellar mass. And this is looking through the whole box, so it's a pretty large statistic over large scales. And then if you look at other redshifts, okay, the picture starts to evolve. You get more and more transmissive sight lines as realization completes. But you still kind of see the signal, right? So here's the most transmissive patch. And again, the most stellar mass is there, the least is here, the least transmissive is here. And then as realization completes, you get a reversion. So this was the most transmissive patch, okay, that had the most stellar mass. And now it's actually the least transmissive patch that has the most stellar mass, okay? And the ones that were very opaque are now actually the most transmissive, and they're just the voids that are now filled with all the photons from the massive galaxies, or from all the galaxies. But okay, so what kind of actual quantitative measure can we make of this? And so I want to talk about one of them just right now, which is the transmission in radial bins around galaxies through the Lyman alpha forest. So you can think of it as, so you have a field of galaxies, okay? And making these fake galaxy pictures in Keynote, I realized that maybe I actually am a cosmologist because I have no idea how to draw a galaxy. You get a field of galaxies, and then you have some quasar behind them, and you draw a line of sight through it, and you measure the Lyman alpha forest in this line of sight. And then for every galaxy, you take radial bins, and you measure the transmission through this line of sight. And you can make curves like this. So it's a bit complicated, but actually if you have to think about it as the anomaly of transmission caused by the proximity of galaxies. So here you have close galaxies, and here you have galaxies that are far away from the lines of sight. And so this is a plot actually from observations from a paper last year. And the blue curve is showing you a slightly higher redshift. And so here you're very close to the massive galaxies that are detected. So on average, you have higher neutral hydrogen, you have higher densities of gas, okay, and more neutral hydrogen, so the transmission is lower than the average. As you get out of the galaxies themselves, you're in the IGM, and you're in the direct vicinity of these overdensities of galaxies, where there are lots of ionizing photons that are already permeating the IGM, so you get a transmission excess. And the further away you go, the more likely you are that you're outside of the existing ionized bubbles and you're in a neutral IGM and you go down below 0, okay? And then you see at a later redshift that where most of the universe is ionized, you still get the proximity density effect, where if you're in more dense gas, you actually have a higher residual fraction of neutral hydrogen, so you get less transmission. But when you go out, everywhere is ionized, so it's all the same, it's all 1. So now I have for you, as an exclusive, some very experimental plots that are kind of crazy looking, but they're quite fun, from Coda 3. And what I wanted to look at was, can you actually see this, okay, with a limited number of galaxies and lines of sight? So it's a similar kind of plot. This is the distance from the galaxies on the x-axis, and on the y-axis is the anomaly of transmission. So above 1 means that you're higher than the average transmission, and between 1 and 0 means you're lower. Okay, and this is at redshift 6, and I take 15 of the most massive galaxies, and only take 10 lines of sight through the box. And then I bootstrap this lots of times, okay? And so what you get is this kind of familiar feature we saw in the observations, right? Where when you're close to galaxies, you're more likely to have an opaque line of sight. And as you get far away, this is the median of all the outcomes, by the way, this dashed line. As you get far away, you move closer to 1, okay? And then very far away, you're actually outside of all the bubbles, so you go back down to 0. You'll notice how massive the scatter is around this median relation, which is the main takeaway for me now, is that you actually need a large number of lines of sight or galaxies in your field to be able to do this. So for now, I think that maybe things like Eiger are going to have a bit of trouble actually working out what the truth is in their work. Okay, and this is just a comparison where I go from 15 galaxies, 10 lines of sight, 15 galaxies, 50. And you can see the banding goes right down, okay? But even with 50 lines of sight, so this is quite unrealistic if you're using only quasars for such a small volume. So this means you'll be have to getting the Lyman alpha forest from the galaxy spectra. You have a huge scatter around here, okay? And that's I think all the time I have. So these are my final slides. Thank you.
Question? Yes?
So thanks, Joe. You're saying that Eiger, it will be difficult, I guess, because they don't have enough galaxies per line of sight.
Yeah.
So what would be the optimal strategy? Like just going much deeper on few?
I don't know exactly. What I can tell you is that so the mass cut, so the magnitude cut in the survey is really important as well, because you bias the effect to more or less massive galaxies. If I do this plot and I take all the galaxies with the perfect sampling, for most redshifts I get a flat line that goes down towards the end. So the cut in the galaxies is really important in determining the signature you get. And yes, I think it is an overall pessimistic message. But I'm still playing with the exact numbers in the sampling. I don't know when it converges properly, how much you can get away with. But the thing is, like, yeah.
Hi, Joe. Thank you for the nice talk. I was just wondering, I forgot the scales on the observational plot you showed before.
Yes.
It seems that they are not
They're not quite the same, you're right.
They are not quite the same,
Yeah,
right?
good catch. Yeah,
So
this goes out to...
It's all over at 10 megaparsecs away.
Yeah.
And your curves...
Well, not quite, because there's still an effect here at the redshift 6 at 15, and then we don't know.
Yeah.
Okay, and wrong way. So yeah, so the observation plot stops here, right?
Uh-huh.
But yeah, still work ongoing.
Okay, thank you very much too. So now it's Pierre Antoine from Observatoire Astronomical Studies, and we will talk about the dust UV offsets in the same simulation.
This way? That's the pointer. Okay. Thank you. So we've had a talk. The first talk of the session was about dust. I'm going to talk about dust again. In the Cosmic Dawn 3 simulation, galaxy formation and reionization, most of what I'm showing here is in a paper which was submitted at the beginning of September and which is under review at the moment.
Very sorry.
Yes?
I forgot again to share the screen on Zoom. So I'm going to do that.
Oh, yeah, yes.
And then I'm not
Go
going to
ahead.
interrupt you.
Okay.
Sorry.
All right, thank you. So most of what I'm going to show you can find in this draft, or in this paper already. Okay. So I'm speaking on behalf of a fairly large number of people who are members of the Cosmic Dawn collaborations. It's an international collaboration with people who have collaborated to various aspects of the project: the production of the initial conditions, the coding, the implementation of various physics, the post-processing, halo finding and scientific exploitation. So quite recently, with the capacity of ALMA to see galaxies at high redshift, redshift 4 to redshift 7, there's one aspect of dusty galaxies which has been puzzling observers and theoreticians. It's the fact that when you look at some of these objects, you see possible offsets between the distribution of dust and the distribution of the UV light. This is shown here, for instance, with this example in the Alpine survey. Okay, so there are some uncertainties in the exact positions of the maximum of the various contributions. But if you take these correctly into account, you still end up with a number of significant offsets between the UV of the galaxy and the dust distribution. Okay, in Rebels, you see this as well. This is a different example with Rebels 25, which is quite a bit extreme, where the dust continuum has its maximum smack in the center here, and the UV light seems to be coming from some sort of structure which is not in the center, but which is on the side of this object. Okay, so so this is seen at redshift 4, 7. The offset can be up to several physical kiloparsec. Okay, and so it asks the question of the multiplicity of these objects, their structure, etc. So there's a number of possible reasons for this, or at least that have been considered. Is it a problem with the astrometric calibration of the observations? Is it a genuine misalignment between the bulk stellar mass and the ISM? Why not? Maybe due to a complex morphology, mergers, or something like that. Is it due to dust obscuration effect? And provided all this, that galaxies don't exactly look the way we are used to have them looking, what can be the impact of all this on stellar mass and star formation rate measurements? Okay. So what I'm going to do in the rest of this talk is use a Cosmic Dawn 3 simulation as an investigation ground to see if we have this sort of effects or not. Okay. It's a interesting testing ground for that because it's a large simulation, so we have a bunch of very massive halos, okay, which is important because maybe the galaxies that we're able to see now with ALMA, for instance, are only the most massive part of the galaxy population. It's also a simulation which is reasonably well calibrated, okay, even if it's more focused on the IGM aspects than the galaxies themselves. But the galaxy UVLF is in principle well calibrated as well, and it goes down to redshift 4.7, so it goes well into the regime of the observation, at least in terms of redshift. And also it's a simulation. Cosmic Dawn 1 and 2 didn't have dust. Cosmic Dawn 3 has a dust model, which I will introduce right now. It's essentially an early version of the Dubois 24 dust model, so the dust model that Johan introduced on Monday, and so we heard about it from Maxime also just before. So essentially these are the same equations that Maxime showed. They account for dust production through two channels, condensation in DSN supernova ejecta and grain growth, and dust destruction through, again, two main channels, supernova shocks and also thermal sputtering. So the idea of having dust in the simulation was, in the beginning, we wanted to see what is the impact of dust on cosmic reionization. Okay, that was the main aspect. But here we're using it for something else. We're using it to look at the structure of dust in the galaxies. The dust is coupled to the ionizing UV radiate transfer. Okay. However, we don't account for the full physics that dust can, through which dust can impact on galaxy formation. For instance, we don't account for dust cooling. Okay. And so this physics has been implemented by Joe Lewis in collaboration with Johan Dubois during his PhD in Raptest Ludaton. All right. So one of the first things that we did with this model is try to calibrate it to have reasonable masses in our galaxies to use for our computations of reionization. Okay, and so this is showing you the dust mass as a function of stellar mass for a number of redshifts. Okay, and essentially our main goal there was to try to make sure that we match the observational dust masses seen by Rebels and Alpine also, I think. So we have such constraints for masses larger, stellar masses larger than 10 to the 8 solar masses, but beyond that, for smaller masses, you don't have that many constraints. Okay. Here we see we have a sort of saturated behavior because of fairly low dust condensation from supernova ejecta, and a fast increase, which you can see here, through grain growth and fairly inefficient destruction. If we leave this model run like this, it actually converts all the metals into dust, which is bad. So in this simulation, we had to, by hand, make sure that the maximum dust to metal ratio is never larger than 0.5. It's a hard threshold that we really set by hand. So let's look at what the galaxies look like. I'm showing here the projection of the galaxies. Okay, this is hydrogen density, the dust column density, stellar mass, and the magnitudes, the UV magnitudes. Okay, red is the proxy for the virial radius. I'm showing the projection and the mid slice because sometimes in the slice you see things that you don't see in the projection. Typically, the big supernova, the big hot bubble due to supernova feedback, you see it much better in a slice than in projection. So it's a fairly massive halo, okay, 6 times 10 to the 11 solar masses. You can see the typical filamentary accretion that you always have in cosmological simulation, the strong supernova shocks and winds, some significant substructure, as you can see. The center is distinctly cool and neutral, okay. And you can see also that you have a very concentrated dust density in this simulation. So what does it mean in terms of UV light and dust distribution? So to get the next plots where the action takes place for these dust UV offsets is really in this very tiny region at the center of the galaxy. Okay. So the simulation, again, keep in mind, it's been done to model the evolution of the IGM during the epoch of reionization and not really to focus on galaxies. So because of that, our resolution, when we look at galaxies, is rather limited, much more limited than in the simulations of Maxime, for instance. Okay. So what I did is I have the 3D distribution of stars, I have the 3D distribution of dust, so I can do the 1D radiative transfer of the stellar UV light through my dust distribution. And I find things like that, okay? Again, this is the very, very center of my galaxies. So it looks blocky because that's the resolution we have, okay, in the simulation. And what you get, these here plots are essentially intrinsic plots, okay? You have the stellar mass density, the dust density, and you have the UV magnitude, okay? And all of this seems to be rather centered. However, when you account for the attenuation of this very massive dust distribution here, very concentrated dust distribution, you get something like that. So in other words, the region which is the brightest in UV intrinsically ends up being so strongly, so severely attenuated that it's not the maximum of the UV light in the attenuated map. Okay? And the maximum of the attenuated map happens somewhere else. Okay? And here you have this sort of flower kind of pattern, okay? With the outskirts of the galaxy appearing to be brighter than the actual center, where most of the action actually takes place. Okay? This is a similar example. Okay? So you do see the sort of offsets that we were talking about in the beginning. Okay? And they are due to severe dust attenuation. Okay? You can see it also in this further example. Okay? Here the center, the brightest part is here intrinsically, but it ends up showing here once you account for the dust attenuation. Okay, and it's not always the case. In some cases, everything ends up being well aligned. Here, even in the attenuated map, you still have all the maxima of the distributions line up on top of each other. Okay, so it's not systematic. It happens, but it's not systematic. So to quantify this more accurately, I've run this on several hundreds of galaxies, essentially the high mass sample of the simulation. Okay, and so you can look at these offsets. I measured these offsets as a function of the halo mass. Okay, and you can see that. So essentially, the offset increases with the mass of the dark matter halo. Okay, there's a wide spread, as you can see. There's essentially no redshift trend that we can really claim at this point. In blue, that's the level, the average offsets that you get in the Alpine and Rebels sample. Okay, so at the high mass end, you get offsets and average offsets in the simulated galaxies, which is similar to what is observed. Okay. Something else which is important is here I noted the spatial resolution of the simulation. So it means what we're seeing in average, this signal is really at the limit of the resolution of the simulation, but it's there. Okay. At smaller mass, it seems to go down. Okay. Here we cannot probe this regime because of the resolution of the simulation, but we cannot rule out that you won't find smaller offsets in lower mass galaxies. Okay, so you may ask, you may wonder, is this offset really because of this attenuation business, or is it maybe just because there's a real offset between the stellar mass and the ISM? So this is the plot where I'm using as a proxy for the near infrared distribution, the stellar mass, okay, and I'm looking at the offset between essentially the peak, the maximum of the stellar mass, and the maximum of the dust distribution. Okay, so if you have an offset there, it really means your stars are offset from the ISM, from the dust. Okay, and you can see that there's essentially no trend here, no mass trend. There's still quite a widespread, but there's no trend with mass. Okay, so that means that the trend that we're seeing here is really due to attenuation rather than a real offset between the dust and the stellar mass. Okay, now as a last plot, I'm also looking at this as a function of magnitude, UV magnitude. And so again, you see expectedly that the offset tends to increase with the galaxy brightness. Okay, and you end up in this rectangle here. This rectangle here shows the Alpine plus Rebels constraint. Okay, and so at this end, in this regime, we are compatible with the Alpine and Rebels constraints. Okay. All right. I think. Did you show me something? Did you show me already the 2 minutes?
Yes.
Okay, sorry, I didn't see it. But I'm done. Okay. So I'll conclude on this. So I showed you that dust UV offset naturally occur in massive galaxies in our simulation due to severe dust attenuation. Okay. The offsets tend to increase with the halo mass and galaxy luminosity. We don't see any trend in redshift. And to quantify this, the average offset is between 1 or 2 physical kiloparsec for masses of 10 to the 12 solar masses halo, or magnitudes at -21, -20, which seems to be compatible with what the observers are seeing. Having said that, you've seen that we're really looking at things which are at the resolution limit of the simulation, which is why it would be useful to look at this also with higher resolution simulations, such as Obelisk, Sphinx. I put New Horizons, but I talked with you and told me that there's no dust in there, so maybe it's not necessarily the best simulation to look at that. It would be nice also to obtain higher order statistics of the offset distribution, both in observations and simulations. And one thing that I did not look at, but which we need to look at some point, is why do we actually find this? How come that we have such extreme dust distributions in these galaxies? And also, why don't we see this at lower redshift? Okay. So these are other questions, other open questions. And finally, just a small advertisement. The Ramsès user meeting is taking place next year in Strasbourg, Observatoire Astronomique de Strasbourg, between the 12th and 14th of May. So if you're using Ramsès, or you plan to use Ramsès at some point, or want to know more, please come to the Ramsès user meeting. Okay. Thank you.
So, one quick question, yes?
Thanks for the great talk. I was wondering, you have a resolution indeed at which you can measure things,
yes,
the cell size, but then there's a resolution. With that resolution, you cannot resolve physical structures.
No.
So how can you address the question whether you have a separation between the mass and the gas?
So you have the dust, you have the distributions that you get.
What
right?
I mean is you cannot imagine forming two clumps, for example, and separated by one cell. That doesn't make sense at the resolution.
No, but you could have. I mean, what do you mean? You cannot have two clumps separated by one cell. You can
because physically in your simulation you cannot form a clump within a cell. So
well, they can't be separated by less than one cell size. Yes, I agree with that.
Okay,
I'm not sure. So
the size of a clump
mm-hmm.
from the it has to be a few cells across to be resolved in any simulation.
Well, it has to be at least one cell. I think we can agree on that, right? Otherwise, how many cells do you think you need? 10, 100?
Typically a few at least, I think.
Well, I think if you go back to the Ramsès paper and look at the gravity solver, you can see that the resolution, the force resolution, is really at the level of the cell. Yeah. And but yeah, like I said, I'm all for looking at this in a more resolved simulation. Yes, but I think if you see the effect really you see the effect at the resolutions. Essentially, I ended up looking at this because when I was making maps for something else, I was making maps of the halos, and I was seeing that the dust distribution was super concentrated, and every time you were trying to do a little bit of radiative transfer 1D, you always end up with these holes in your maps. And then in Stockholm, I saw this, the rebels thing, and I thought, wow, maybe this has something to do with what we're seeing here. Yeah. But the question of resolution, how many cells do you think you need to resolve one thing or the other thing? It depends on the physical processes that you're looking at, I would say. And here is just a matter of having stars piled up at the center of your halo and having a dust distribution which is, how do you say, sharp enough that it's going to punch a hole in your UV map. Yeah. So I think you're going to see that as soon as you have a dust distribution which has a much stronger peak, let's say, than your UV flux, I would say. And so I think you should. I would expect that you see that at higher resolution as well.
We see offsets everywhere in the high resolution simulations. It's between the UV and because of attenuation and because the IFM is structured in many star-forming clumps, and some of them are completely
that as well.
And some are not, and that's what I mean. You don't resolve these star-forming clumps. And so where does this come from?
Well, so what you do resolve is this sort of differential, the difference between the stellar. Sorry, what was that? the difference between the star distribution or the UV light distribution and the dust distribution. I think the main point is that one is rather extended, whereas the other is super peaked. And I think that's what makes this. And I think you're going to still have that in higher resolution simulation.
So thanks, Pierre. Okay. Let's move to the talk of Marion Parfum. She works on the impact of AGN-driven wind on massive galaxies in the early universe.
Yes. Okay, so hi everyone. I am Marion, a postdoc at EPFL in Switzerland. And indeed, I'm going to talk about simulations of high redshift galaxies and AGN feedback. How is it working again? Yeah. So just maybe to make this clear at first, here I will be focusing on cosmic times that are beyond cosmic noon. So basically focusing on the formation of the first gravitationally bound structures, halos, galaxies, stars, and supermassive black holes. Because we can now target these things with the James Webb Space Telescope in particular, and because, well, we have lots of interesting questions to answer, such as these ones here. First, how does these things formed at first, so the black holes and the galaxies? How did they co-evolve? And in particular, these specific questions I will be interested about for this talk, which is how so early in the universe can we form so massive galaxies and that yet do not form stars anymore? So that's one quick example here. So what you have is star formation rate histories for two galaxies that have been observed with the James Webb. So they are relatively massive at this redshift, redshift 5, redshift 3, with more than 10 to the 8 solar mass in stellar mass. For example, this one, you can clearly see a burst of star formation, after which, so very quickly, a few 100 million years, there is no star formation again, so that's a quiescent state, at least at the time of observation. You have something relatively similar here regarding the error bars. And yet, in both cases, we have hints of AGN feedback. So, for example, with elevated N2 over H alpha ratio, which is specific for the radiation feed from the supermassive black holes. Broad H alpha lines, also specific from the outflows driven at these velocities mainly by AGN, so supermassive black holes again. So we could think that we understand the picture and what happens at high redshift, but yet, if you look at the number densities of massive quenched galaxies at high redshift, between 3 and 4 here, so that's the number densities from observational surveys, the most recent one of the most recent ones being this one in red. And if you compare this number of massive quenched galaxies with the number found in simulations, in the bottom panel here, you already see some discrepancy. So, okay, redshift is kind of comparable, but the higher the redshift in simulation, the less we find these objects. And actually, above redshift 4, you barely find any massive quenched galaxies in simulations. So the question is, why? What is the physical origin of a massive galaxy quenching at redshift above 3, let's say? And why do we fail at simulating these objects? So to try to answer these questions, I will focus on one such simulation, which is Illustri's TNG. So what you have here is a specific star formation rate as a function of stellar mass. That's a work that has been carried out by an undergrad student in our group. Basically to show you that at redshift 3.7, this is the number of star-forming galaxies that we have. This is the number of quenched galaxies that we have in this simulation. Why redshift 3.7? Because the snapshot before that, we have no quenched galaxies at all. So what is the cause for this process? There are 3 possible explanations that we explored. So we could think that depending on galaxy mergers, so major or minor mergers, that could provoke some starburst after which you quench star formation for a while. So we could think that there is a difference in galaxy merger history from star forming to quenched galaxies, but it appears to not really be the case. So if you count the number of merger events at this redshift range for both populations, there is no clear difference. We could think of the large-scale conditions. So if you reside in an overdensity, if there are more galaxy satellites or more gas available overall for forming stars, for feeding the black holes, you could expect maybe to stop forming stars earlier. But again, that's not really the case. So they have very similar environments overall in average. And the last process we could think of is AGN feedback, mainly because we think that's how
massive galaxies locally at redshift 0 are actually regulated. So we think that the energy coming from the accreting supermassive black holes is able to stop forming stars and to regulate both black hole and galaxy growth. So what we can do is to resimulate a few of these objects and just turn off black hole physics. So that would be a hint of whether black hole physics at this redshift is also capable of impacting star formation. So I'll focus just on one object here, but I've done the same exercise with a few of them. So that's one of the quenched galaxies from the plot before. That's the star formation rate as a function of time. The black curve is the fiducial halo, so that's a resimulation of this specific halo with the TNG physics and resolution. And in red, that's without black hole physics at all. We don't form black hole, no accretion, no feedback. That's the property of these galaxies, and you can clearly see that in order to suppress star formation at this redshift, we need black hole physics somehow. But to go a bit further, so we may need AGN feedback, but how about how we model this in simulations? There are plenty of AGN feedback models. We rely on subgrid models because we don't resolve the scales at which accretion and energy release happen. We want to couple that with galaxy scales as well. So that's how AGN feedback is implemented and works in Illustris TNG. We have a bimodal model where at high accretion rates, so which is more relevant for the high redshift because you have more gas, so higher accretion rates for the black holes. The energy is released as thermal energy, isotropically, around the black hole in the gas cells that surround him. While when we go to a certain threshold, in the low accretion rate regime, mainly relevant for the low redshift universe, we go to a more efficient kinetic jet mode, which is meant to quench massive local galaxies by construction in this model, where we will kick all the gas cells in a random direction, so imparting them a certain velocity. That's the TNG model. My point is, if I now resimulate the same halo, but just focusing on the quasar mode, so the high redshift feedback mode, let's say, that's the green curve here. You see barely any difference between the no feedback, no black hole case and this AGN feedback model. Meaning, if we want to suppress star formation, at least in simulations, this is mainly because of the low redshift mode that we have been relying on. You can also see it from the dotted vertical line here, and it's quite clear that once the jet mode kicks in, star formation rates decrease and the galaxy is considered as quenched. So, yet this seems to be quite a numerical artifact. It doesn't really tell us whether AGN feedback is or not able to regulate galaxy growth at high redshift. So what if we try to better model AGN feedback in this regime? So first, this is an idealized galaxy that you see edge on, just to show you how the TNG quasar mode works. So that's the actual model. And so yeah, here it is. You maybe don't see a lot of differences with time. The black hole is accreting. There is no clear evidence for AGN feedback here. And in particular, there is no wind. While we do accept, and especially at high redshift, signatures of AGN-driven winds. So that's one example here from 2014 already, so that's not new. You can see that's the broadening, basically, of some lines that are driven by the AGN radiation. And if you look at the most massive galaxies here, and in the nuclear region in particular, you do see the broadening of these lines. So there are hints of the presence of supermassive black holes in those massive galaxies, and at the same time of high-velocity gas, so of AGN-driven outflows. So let's try to model these outflows. That's what I will be calling the Mistral model, because Mistral is the name of a wind. And so now the idea is to switch from this quasar mode thermal energy release into a subwind modeling of AGN-driven wind for the high accretion regime. So it's inspired by a model that was implemented in Gadget, and it's now implemented in Arepo, this Mistral model. And it relies on the fact that on its journey towards the black hole, not all the gas will be accreted. Some part of it will be kicked, driven by radiation or whatever process, into a larger scale wind, emerging from the broadline region that is not resolved in simulation. So that's why we need to rely on subgrid model, try to model the outflows at larger scales. And to do that, we will kick stochastically a few gas cells around the black hole in a direction that will be along the angular momentum of the gas within this region. So that's the basics of the model. We will kick those gas cells at a certain velocity that we choose as an input, and we can play also with the coupling efficiency of accretion and feedback. So how much winds will be released from the accretion process. And that's now the difference between the TNG quasar model and the Mistral model. So same galaxy hadrons, that's the gas density. And now you can see from time to time when there are AGN feedback events episodically, bipolar winds that emerge. So it's hot and very diffuse gas constantly along that direction here because it's an idealized galaxy. So the angular momentum is always in the vertical direction. But that's just to show you that we do produce some kinds of AGN-driven winds in this idealized context. So now, what we are interested in is massive quenching at high redshift. So we need to go back to a cosmological context. So I'm going back to zoom simulations of TNG galaxies, focusing for now on 3 halos only. And just to show you that Mistral is producing kind of realistic objects, so that's the stellar mass-halo mass relation at redshift 2. The black symbols are for 3 galaxies that do not have black hole physics. The green counterpart is with the previous TNG quasar model, and in purple you have Mistral. So here we do regulate quite realistically star formation at redshift 2. And by construction here, so we kick cells at 10 to the 4 km per second, which is kind of the velocity we expect from winds in the broadline region, but still the outflows are not launched at this velocity because just one cell being kicked, the outflow will have something around a few hundred to 1,000 km per second in velocity. And so here, approximately a third of the inflowing gas mass is accreted by the black hole. The rest is driven as a wind, which was not the case with the thermal model. And for the black hole mass also, because we don't want to produce a supermassive beast or undermassive, so that's the black hole mass stellar mass relation. You have the scaling relation from observations here in dotted and dashed lines. And again, so we are not very far from these relations. Even though they are for redshift 0 observations, it still gives a hint that the black holes are somehow realistic at this redshift. Now going back to even higher redshift, we can have a look at the star formation history and if or not those AGN-driven winds can impact star formation early on, especially above redshift 3, which is quite hard currently in simulations. That's my 3 galaxies. Going back to specific star formation rate, because basically with this gray line here, so being below these lines means we are in a quiescent state. So that's kind of a threshold, theoretical threshold for distinguishing between star forming and quenched galaxies. So the galaxies don't have all the same star formation history, but you can see in any case with Mistral those peaks, those bursts of star formation, and then the galaxies goes into a quiescent state, let's say. So I think the interesting thing here is if we were to observe the galaxy, say, at those specific points, we would flag the galaxies as quenched, even though in reality it could rejuvenate, and that's what happens in the simulation. And you can see from the 2 other setups, no black holes or TNG that we don't have the same burstiness, and that we will not be able to explain this feature. So that was 3 galaxies. We can try to do better. The idea would be to have a statistically complete sample as best as possible of massive galaxies, so targeting all the most massive galaxies from the TMG 100 box, which is a box of 100 co-moving megaparsec, and increase the resolution. We are doing zoom simulation, so why not changing physics and increasing resolution? So going to the TMG 50 resolution, which is 8 times better in mass. So having few tens of galaxies with Mistral and the previous models, and try to see, to determine whether or not AGN winds at high redshift can explain massive galaxy quenching. There are other things to improve, of course, so especially at this high redshift, we'll be very dependent on when and where we seed the black holes, so we could improve the black hole seeding, black hole accretion scheme, and obviously also implementing a better model for resolving the ISM. So that's different things that are currently under development by different people. And that will be my summary. So, can AGN feedback quench high redshift galaxies? You can tell me if you're convinced or not. I would say that we should not discard this pathway. So, a summary of what I said is that currently cosmological simulations have a hard time reproducing what we do observe for this specific object. And that's mainly because of how we model the physical processes underlying. So the TNG quasar mode, when we rely on thermal energy only because it's quickly dissipated, it does not really impact much, neither the black hole or the galaxy evolution itself. But if we try to model the black hole driven winds, we do see an impact at high redshift. And that's maybe one of the key points I would like to address also. We may need to go beyond models that we calibrated and use for redshift 0 observations if we want to understand the full picture through cosmic frames. Yeah.
Thanks, Marion. Someone has a question? Yes?
Maybe I'm missing something, but it seems like the Mistral model is kind of in between the quasar mode and the jet mode. And it seems that it has an effect that is in between the quasar mode and the jet mode. Is that
Yes.
the case? Or?
Well, it's similar to the actual jet mode in the sense that it relies on a kinetic prescription. One of the maybe two big differences is that we do not accumulate energy until we reach a certain threshold, for example, which is the case for the jet mode actually. So now that's not the case, it's just naturally dependent on the black hole accretion history. And also, we inject, we kick the gas cells along the angular momentum because that's supposed to be the path of least resistance. It's kind of a natural way for reproducing those bipolar winds. In TNG, actually, with the kinetic mode, it's just random directions for all the gas cells. It's not, I don't know if we have to be bipolar, but that's one of the key differences. Yeah.
Sorry, we don't have time. But thanks, Marion. So now let's move to Andrea Saccardi, who works on exploring the natural gas of high redshift galaxies with GLPs.
Okay. So, good afternoon, everybody. I am Andrea Saccardi. I just finished my PhD last week at the Observatoire de Paris at JP, and in November I will start a CNES fellowship at CEA. Thanks a lot to the organizer, to PNCG, and today I will talk about gamma ray burst and how is it possible, thanks to gamma ray burst, to explore the neutral gas of high redshift galaxies, in particular gas components, metals, and dust. So let's start with a bit of context. There were already several talks before about the distant universe. So, according to the cosmological lambda CDM model, the formation of the first astrophysical object happened around 200 million years after the Big Bang, around redshift 30. They decreed the end of the so-called dark age, since they are the first source of photons that ionize hydrogen and the first source of chemical elements heavier than hydrogen and helium. So they transformed the universe from its initial state of simplicity, so-called zero metallicity, into one of increasing complexity. So understanding their role is crucial, above all from the point of view of the chemical enrichment of the universe. So what is the current state of the art concerning high redshift galaxies? The advent of JWST is revolutionizing the field, allowing the observation of galaxies up to redshift 14. You see here an example of a galaxy at redshift 14.3, where you see the Lyman alpha break, but the faintness of these galaxies limits the available diagnostic even for the incredible capabilities of JWST. Indeed, we have still few constraints on the neutral gas, which is main component at high redshift that retains the majority of metals. And gamma ray bursts are ideal tool in order to explore the properties of these faint high redshift transforming galaxies. How is it possible? Is it possible thanks to absorption light spectroscopy of bright background source like a quasar or gamma ray burst? In this case, the radiation emitted by the gamma ray burst travel along the line of sight up to telescope ground based that follow up the detection of the gamma ray burst by acquiring absorption spectra, not only of the intervening system as you do with quasar, but also of the host galaxy of the gamma ray burst. Gamma ray bursts are ultra-relativistic jets produced by by a newborn accreting compact object. They are divided into two classes: short GRBs linked with the merging of two compact objects, and long GRB associated with the collapse of a massive star. They are characterized by a prompt emission that lasts a few seconds, detectable in gamma ray thanks to the space satellite, that is followed by a bright afterglow emission that is due to the shock between the jet and the interstellar medium. Is detectable at all the frequencies, and the afterglow emission lasts from hours to years depending on the frequency range. Focusing on long GRBs, they are extremely bright at redshift, as I said, associated with the collapse of a massive star, so we can trace star formation up to the highest redshift. And another important advantage is the fact that the afterglow emission fades. So we can study also the long gamma ray burst host galaxy, thanks only to the explosion of a gamma ray burst without any selection in luminosity as in galaxy survey. So we have the opportunity to link the information on the neutral gas obtained in absorption with the information on the ionized gas that we can obtain in emission and the continuum of the long GRB host galaxy. Here you see an example of absorption spectrum for a galaxy at redshift 4 with only 1 hour of observation. You see the Lyman alpha in absorption, so the absorption due to the neutral hydrogen of the host galaxy, the Lyman alpha 4, so the absorption in the intergalactic medium, the Lyman limit. Red side of the spectrum, a longer wavelength compared to the Lyman alpha in absorption, you see the absorption lines due to the metals. And this is for a galaxy that is not detected in HST image of the field, R magnitude limit 28.5. So this to underline the powerful potential of long GRB to have access to the detailed information on the neutral gas. And from the analysis of the absorption spectrum, we can measure two fundamental things: the redshift of the absorbers, both of the host and of the intervening system, and the column density of the ions of different chemical elements, from which we determine the chemical abundances, and then in order to study metallicity and dust depletion, calculate the distance of the corresponding gas cloud, so each component of the neutral gas, study the kinematic of the gas and the chemical abundance pattern. And this is what I do within Stargate collaboration. I'm co-I of an ESO large program in order to perform a follow-up with optical near-infrared telescope. And today I would like to speak about GRB 21905A at redshift 6.3. We took an X-shooter spectrum at the VLT after 2.5 hours from the GRB trigger for exposure 1200 seconds, covering this huge wavelength range thanks to the X-shooter spectrograph. And here you see the 2D trace of the GRB afterglow, and on bottom you see the 1D extraction. So you appreciate here the neutral hydrogen absorption, so the Lyman alpha in absorption, and the absorption lines due to the metals. Going deeper into the spectrum, you see here the identification and the fit of all the absorption lines. Low ionization lines like iron 2, carbon 2, silicon 2, high ionization lines, carbon 4, silicon 4, nitrogen 5, and fine structure line. This is really a complex system in terms of velocity structure. There are two big clamps, A and B, separated by 300 km per second. The overall galaxy is formed by 6 components covering 360 km per second, and there are fine structure lines in both clamps. I have performed a detailed analysis on metallicity, chemical enrichment, and dust depletion. Actually, I don't have the time to go into the detail of the method, but for the overall galaxy here in the y-axis you see the element abundances, while in the x-axis you see a parameter that tells us how refractory is an element. And by performing the fit, we can retrieve two important information, which are the slope, zinc over iron, which is a dust tracer. So it tells us how strong is the dust depletion inside the galaxy. And the intercept at x equal to 0 tells us the total metallicity corrected for dust depletion. In this case, I took into account also alpha element enhancement, given that redshift 6.3 is reasonable to take into account it, given the fact that supernova type 1a didn't have time to explode to release in the surrounding medium element like iron. So here we have determined total metallicity and zinc over iron. Then the deviation here from the linear fit, after correcting for dust depletion and after taking into account alpha element enhancement, are due only to nucleosynthesis. So we can produce an abundance pattern, so here X over iron due only to nucleosynthesis. There are some lower limits due to the fact that the line in the spectrum are saturated, and the violin plot are a propagation on the dust depletion error. I've performed the same kind of analysis also component by component, so the seeds component that I've shown you before in the spectrum. The method is the same, but with a slight difference. Actually, in the y-axis now, we don't have any more the information on the neutral hydrogen, given that we are not able to split the Lyman alpha absorption in different components, but we have still the information on the dust depletion. So we can see if there are some components with more or less dust respect to others. I have produced also the chemical abundance pattern for each component, and there are some peculiarities like aluminium overabundance component 2, 3, and 4, which is not the first time that we found at high redshift in a GRB host galaxy, together with oxygen underabundance component 3 and component 4. These peculiar abundances are typical by comparing this abundance pattern with local stars of stars that are found in globular clusters and dwarf galaxies. And the best candidate in order to explain this kind of abundance pattern are massive AGB stars and fast rotating massive stars, which are actually the progenitor that we thought are of long GRBs. For GRB 21905A, we got also an HST image of the field. You see 250 days after the GRB trigger. Here you see with the white cross the position of the afterglow. With in black you see the Ishute slit for reference. And here you see the host galaxy, redshift 6.3, together with 4 nearby objects. And the first time that I saw this image, I would like immediately to understand if these objects are at the same redshift of the GRB host. So this fueled the desire of follow-up observation. We got a second HST epoch in 2 different filters, and I could claim that the delta object is at lower redshift, since it's detected also in the filter at 775 nanometer, while the other are not detected, so actually at redshift greater than 5.7. And I would like also, I will do it, I will submit a JWST proposal in order to, last cycle we fall in the first quintile, but we didn't get time unfortunately, to detect auroral lines in order to determine spectroscopically the redshift of the nearby object, look for the presence of a possible galaxy group at high redshift, clamps interacting system, and studying, as I said before, different phases of the gas, the neutral and ionized, and link them. I'm the PI of an executed Muse proposal. I will analyze the data soon. In order to detect Lyman alpha emission, we have a tentative detection in the afterglow spectrum of the GRB in order to determine the Lyman alpha spatial distribution and look for the presence of possible Lyman alpha blobs extending over this possible galaxy group. So putting together GRB 21905A in a more global picture with Milky Way metallicity, quasar DLA, and gamma ray burst, even if the statistics is not so high, I hope that I've convinced you that thanks to gamma ray burst afterglow spectroscopy, we can reach high redshift universe and populate the reorganization era. Recently, there were other 2 gamma ray bursts at high redshift exploded. One is redshift 6.78. There is a paper in preparation, which is the highest redshift for a GRB afterglow determined from metal absorption lines. And the other one is the first Einstein probe GRB, which is actually a new satellite that was launched in January, at redshift 4.86. With this picture in mind, we have a main limitation, which is that we have still a poor fraction of GRB with optical and near-infrared afterglow, let's say 20–30%. And in order to overcome this limitation, SVOM is a new French-Chinese satellite that was launched last 22 of June, and one of its goals is to boost to 50–60% the fraction of GRBs with redshift determination and enhance the number of high redshift GRBs. Here you see the spacecraft, the payload, 4 instruments on board, the gamma ray monitor, gamma ray telescope, X-ray telescope, and visible telescope. And this is the first mission with a dedicated ground-based observation, to perform the follow-up with a wide-angle camera and 2 follow-up telescopes, one French and one Chinese. How SVOM will be able to reach such a goal? First of all, the energy threshold of the gamma ray detector at 4 kV may enable the detection of faint soft GRB, likely at high redshift. There is a good sensitivity of the onboard optical telescope in order to detect and localize GRB afterglow, and will permit also to rapid pinpoint to high redshift candidate, 22.5 in 300 seconds. SVOM GRB are all observable from Earth, 10 to the near antisolar pointing, and as anticipated, there is a dedicated follow-up from the ground, in particular in the near infrared, crucial for the high redshift, with a French ground-based telescope, which is called Colibri, that will arrive at 1.8 micron. A revolution could be played in GRB science, but not only, with Theseus, which is a new space mission selected for ESA M7 Phase A, actually 2037. If you see at this plot, if you look at this plot where I'm showing you the energy peak of the prompt emission of the GRB as a function of the flux for already detected gamma ray burst with current and past satellite, and in gray you see a simulated GRB population, highlighted in yellow a GRB population at redshift greater than 5. And you see that in order to detect high redshift GRBs, you really need a detector that works in the softer energy band, and you need to go down in flux, thermosensitivity. And this is the case of Theseus payload with a soft X-ray imager, amazing X-ray localization, large X-ray field of view, an X-gamma ray imaging spectrometer, and an infrared telescope on board that will be able to do low resolution spectroscopy. So we'll be able to obtain redshift from the space. And the situation will change on this direction. In gray you see gamma ray burst detection with redshift in more than 20 years of missions, and with Theseus 3.5 years, so the nominal duration of the satellite, we will be able to cover the reionization era for between 40 and 80 gamma ray bursts at redshift greater than 6. And if Theseus will revolutionize the GRB science from space, on the other side, as anticipated this morning, Andes will revolutionize the ground-based spectroscopy. Andes is a high-resolution spectrograph that will be installed at the ELT. I'm part of the working group number 3. And thanks to Andes, we will be able to reach the signal-to-noise level that we really need to study faint redshift sources, resolve narrow absorption lines, in particular constrain the column density of key elements that are important in order to determine, for example, the dust, which is, for example, zinc, and finally to study relative abundances in individual gas components, as I've shown you before, but with a quantitative comparison with nucleosynthetic models for different masses of the projector. And with this, I think that I'm finished, and I leave you with my conclusion. Thank you very much.
So maybe one quick question, because we are a little bit late. So. No? So thank you.
Perfect.
Olga.
Thank you.
Let's move to Romain Lebon, who works in simulations of early structural formation.
Let me in. Okay, let's keep. Shall. Hi everyone, I'm Romain Lebon. I used to be a PhD student in Lyon with Joachim Rosal and Benoît Commerson. And today I'm going to present you
the two main works of my thesis. So this is about okay. The thesis is about the first stars, formation of the first stars. So we all know this picture of the universe started with the Big Bang, and now we are here. And where did the first stars form? After the Dark Ages, here, around 1 million years after the Big Bang. So before we have no stars, no galaxy. Over density start to collapse, and then we have the first stars. Redshift 20 to 30. So very high redshift. We do not have any galaxy. We just have filaments of gas that are collapsing, and mini halos where the first stars start to form. So that's why the formation link cosmology to star formation, because you have initial conditions that are purely cosmological, and then you are going to the star formation scale, and that's why you can have it's a link between these two physics. Main particularities is there were no dust, so we have a metal-free gas at that time, and the gas is only made of hydrogen, helium, and tiny fraction of deuterium, and extremely tiny fraction of lithium, which make it negligible. So the main difference is that we do not have metals to cool down the gas, so we are only H2 and Hg, which are very less efficient coolant, and also we need to form them, so we need to solve the chemistry. The animation. So the main particularity of this star is that we observe the formation of a disk at a high density, and the primordial gas is highly susceptible to fragment because it has no metals. So there is no opacity that can have the collapse. So you need to, if you do numerical simulation, you need to follow the gas to much higher resolution to really have a true picture of what is happening. For example, this is a simulation I run. You can see there is multiple fragmentation. And if you want to resample the IMF, you need to take this into account. So it makes simulation much more difficult than for present-day star. So the main question about this star is what is their mass? Were they massive or not? First we thought they were quite massive because of the lack of metals, and now the picture is more blurred. Fortunately, there is no observation. For example, this is a study of only a numerical simulation. You can see there is a 5 order of magnitude broad between these 6 studies that all are including different physics. One of the differences is with or without relative feedback. You can see that relative feedback tends to increase the mass because it limits fragmentations. But mainly, there is a huge scatter in the simulated IMF. So this question is still open. First project of this thesis was where did the first star form? So we studied the initial conditions, and then I will focus on the impact of relative feedback. So if we want to know how did this first, so why do we not want to know why is the first star formed? Because we see that the collapse speed and chemical abundances can have an influence on the collapse. So the collapse speed, for example, can depend on the geometry of the cloud and the angular momentum, and the chemical abundances may depend on the initial condition of the chemical initial abundances. So we can have also an influence on the chemical network we are using. And if you want to run isolated collapses, then we need to know precisely the initial conditions in which the stars were formed. So to do this, we use a code Ramses, but we need to add non-equilibrium chemistry to Ramses. So we just have a system of equations. So for example, the equation of different species and the gas temperature will depend mainly on the cooling of H2 and Hd and other terms. And this is a huge system because we have plenty of reactions, and also it's a stiff system, making the numerical integration a bit tougher. So we use the Chrome, which is a solver that can be used for this. And we merge the two. So this is a coupling that takes some time, so it slows down the code by 2 to 3, a factor 2 to 3. And we use an updated chemical network because this is the only physical part here, so coefficient rate. And we use a new chemical network from Fourier time. So we have 11 species, meaning we have 11 Bassett scala, which is huge, and we have 23 reactions, meaning we are solving 23 a system of 23 differential and link equation, or differential equation, which explains why it's a bit slower. So what are the physical and chemical properties? Well, so what we want to do is to run a cosmological simulation to solve this question, and with non-equilibrium from initial chemistry. So we want a fairly small box, but with a very high resolution. You can see that here the resolution limit is very low, 10 to the 4 solar masses, and quite a decent resolution. But because we stopped our simulation at shift 18, so we do not go very fast, very long. And you can see the evolution of the simulation in this movie. So mainly the idea that we will have plenty of birth sites of the primordial stars, and so we can have statistics on the initial conditions. For example, this is a map of one halo. You can see temperature, density, and H2 abundance. And you can see the temperature is lowest at the center because we have H2. You can see here the density peaks. Now we have identified many halos in our simulation, so we can do statistics. For example, we can identify halos where we observe star formation. So we can have a criteria saying that the gas is collapsing. That's what we do here with halo where we observe a clamp that is collapsing, and halo without. So we have the red point and the blue point. This is H2 abundance versus the zero temperature. And you can see that we have a clear threshold, the H2 abundance, above which we always observe a clamp. And the temperature of halo nearly a proxy for the mass of a halo, so we observe this curve. Mainly the main point is that we observe a clamp above a given threshold of 3 × 10⁻⁴. So that's it. And then we can also study the importance of the different cooling species. So there is H2 and HD, two are molecules. Deuterium is much less present, but in the literature, HD is a bit more efficient to cool the gas, especially at lower temperature. So we observe a scatter in our simulation, so nearly 10% of halo with higher HD over H2 fraction. And what we observe is this is a plot temperature versus density and HD over H2 ratio over the density, and each line is a halo. So we have plenty of halo here, and we can observe that halos that are HD rich, so halos that are more yellow, tend to be colder, meaning that HD cooling is important, and it cannot be neglected. And it is especially in the Q in the range 10 to 2, 10 to the 5 particle per centimeter cube, as we can see here. The takeaway is that the HD is not uniform, HD abundance is not uniform among all our halos, and that the cooling is not negligible. So the question we can ask is what is the cause of higher HD abundance in some halo? And it tends to be that it has a link with spin parameter. The spin parameter can be a measure of the degree of rotation of a halo, and a higher spin parameter can mean a slower collapse, which can lead to a higher HD over H2 fraction. So we can see this as a plot. This is the spin parameter versus the ratio HD over H2, and there seems to be a slight trend linking the two. So the idea is that a slower collapse might trigger HD formation, and it can be understood because HD formation is triggered at lower temperature. So this link can be important. So that's it for the first part. So the new cosmological simulation. So we have some clues and constraints on the properties of the halo, for the H2 abundance, and we have also observed different HD abundance. So if we want to do isolated collapse, we need to take into account the variation in the initial condition of the whole system. And now we skip to the second part of the thesis, which was about high resolution simulation, where we truly form the stars, and we also include relative feedback. So the methodology is we want to start from initial cosmological initial conditions. As I told you, it's important because there is a scatter. So we choose. However, the issue is that our box is only 70 kiloparsec wide, and it's not visible with Francis. It's visible, but not. It's too time consuming to have a 23 level of refinement. So we need to find a solution. We can do zooms and then extract the full parsec. So meaning, for example, this is a zoom simulation. You can zoom in, and then we extract only the center 2 parsec of the simulation. It's a bit technical because we need to reconstruct the IMR grid for Ramses, but we did it. So the idea is that when we have this, so we completely lost the large-scale structure. But the idea is that if what is happening in this small box is sufficiently fast, then this is valid. We include radiative feedback. So radiative feedback for Pop3 star can do a photoionization and photodissociation. We can have a formation of a bubble of hot ionized gas and formation of a region of H2 close to the stars. The consequences of this is not well understood, but overall it tends to reduce star formation, fragmentation, and thus we have larger mass stars. So if I come back to this, we need to couple now every outer equilibrium chemistry and the evolution of the number of photons, Ni. So this is making the system even much tougher because we have again new new reactions. So this is because we add the number of photons per beam. So this is the system we are solving for each time step and each stellar Ramses, and this is much longer. And so we use Ramses RT, but with non-equilibrium chemistry and photochemistry. And so just a proof of concept of this is that you can observe here we have a sink that is emitting photons, and you can see that we have a depletion of H2, which tends into a higher ionization fraction and higher temperature. So the impact of radiative feedback is visible. We observe photodissipation and photoionization. And we can also do try to understand what can be the impact on the true simulation. And for example, this is the result. So for 1.6 AU resolution with and without RT. Radiative feedback tends to slightly reduce the total mass because it adds pressure, and so there is less gas converted into the sink. So it's a preliminary result, and we need to do more simulations and to integrate the simulation for a longer time. And that's it. Thanks.
Small question for Romain. Yes?
Maybe very technical. How difficult is it to extract a region? Like, can I do that for LG simulation?
Yeah, we tried to do it. It was a bit tough because the main point is that you have cells of different sizes in Ramses. So either you oversample everything and then it's too large. And we did some embedded cube, zooming on the center object. And so it can be. I do the code, and I think it can be used for anything of Ramses because it buys our MR2 cube. And you can try it if you want. I hope it's feasible for anyone, but I didn't try.
I think you made it public on your.
Yeah, it's public, so you can try if you want.
Okay, thank you, Romain.
Yeah.
And for the last talk today, Yami, Mamu,
Can I do this? Because I'm only 17%. My charging wasn't working. I don't know why. My computer's old. That? Oh yes, of course. Thank you. I forgot to share my screen. Okay. Share. Share the screen. Okay. Good.
Excellent.
Look at this. Oh God.
its grade.
Oh yes.
Okay. So I also thank the organizer for inviting an old-timer like me. I think I'm the oldest speaker at the conference and perhaps the oldest member. And thank you for your patience because it's getting late and you want to all go home. So, sorry. So this is work that, a 2-month project by an undergraduate who's now starting a master's at Cambridge, and which we hope to publish in the next few weeks, on the issue of whether radial segregation of colors in star formation is reversed at higher redshift. So what am I talking about? I'm talking about the fact that star formation is enhanced under circumstances that are typically external. That is, that you have either gas inflows that are very robust at one point, maybe you're crossing a filament, or that you have gas-rich mergers. At the same time, star formation is suppressed by a variety of mechanisms, some internal and some external. And among the external ones, you have ram pressure stripping of the outer gas that would otherwise fuel all the way in, which we call starvation, or you have ram pressure stripping even of the inner gas in more extreme conditions where you strip out the ISM and even the molecular clouds. It's very difficult to do. And you can also have a new idea that you can have also blowing out the gas or pushing out the gas or heating it up from the central AGN, that is the AGN of the central for satellites. And finally, when you have gas-rich mergers, at the beginning you boost the star formation, but then you boost it very efficiently, and afterwards you become very passive. So to understand radial segregation, you have to understand how these aspects, how the enhancement and the suppression of star formation are competing. Okay, let me try this. Okay, so we've known for a while that we have a color and star formation segregation, all right, since Osterbrock 1960. Of course, we've known about morphological segregation since Hubble, okay? And furthermore, we've known, so this is a global segregation I'm talking about, that cluster galaxies are less star forming. And we also know that as we evolve in redshift towards higher redshift, they tend to be bluer galaxies, okay, the Butcher-Ulmer effect. We've also known about radial segregation, mainly thanks to Mike Balog, among others, but I think he's the one who first showed it convincingly. So here the fraction of emission line galaxies is higher at large radii from clusters. And at the same time, he also showed that the fraction of blue galaxies, which is 1 minus this, so the blue galaxies are predominant in low surface density regions. This is the fifth nearest neighbor. Okay. And so I thought that there were only 3 or 4 studies that had been done on this. I was aware of the early ones, and I thought that was it, okay. And I asked Olga Kuchati, do you still, well, she gave a talk where she said she didn't believe in her no more. Like she didn't say that. She said, nobody can reproduce my point here, which found a reversal at redshift 1.3 of the star formation segregation. And I asked her for references, and she gave me 1 or 2, but my student found 36 since her paper, okay. And I subdividing them by how they measure the specific star formation rate, what proxy they use, and what proxy they use for density. And what you see here is that there's a huge diversity, okay, with a bit of a trend towards, with time, to higher redshifts where reversals may occur. But by the way, some are upper limits rather than lower limits, okay. So how could all these brilliant people disagree? Okay, how come we haven't solved the problem yet? So there's several reasons for this. Okay, one is sample selection. Okay, so we tend to select starburst galaxies are very easy to visualize, right? We would like to have a mass-weighted selection rather than a starburst luminosity, so ultraviolet luminosity selection. So we have to be careful. Second, okay, we have to make sure that the SSFR indicators are robust to K-corrections, if you wish. Third, the density indicators, local versus global versus radial, are not telling us the same stories. They're probing different astrophysics. So we have to keep this in mind, it's very important. Fourth, we have statistics and projection effects, and I'll show it in the next slide. And fifth, we have cosmic variance, so we need large samples. So here's an example which I think might or might not be a source of a problem. So this is one cluster here, okay, of about 500 kiloparsec radius, okay, where you have a red clump and a blue clump of galaxies, okay. The yellow points, I'm sorry, I don't show it here. The yellow points are the ones that have spectroscopically confirmed redshifts. None of them are in the clumps. And so I wonder whether we're not seeing small groups that are superposed along the line of sight. Now, of course, these galaxies have photometric redshifts that are consistent, okay? It's not like a completely chance projection, but there might be, within the uncertainty of photometric redshift, it's not difficult to get chance projections, okay? So we could have, so do we have several groups and possible projection effects? I don't know, but it could be. That's why we have to be very careful. So our method is that we use hypersuprime CAM EDR3 with such a huge solid angle. We use GRI-ZY down to about 24. We use U minus B rest frame, as many others have done, for a specific star formation rate. It was a quick choice. We probably could do better. Okay, and the density we do by doing two ways: fraction of red galaxies and the scale radii. The comparison to the scale radii, the NFW scale radii between the blue and the red populations. And we do this for 4,000 clusters called Chimera clusters. Okay, so this is the HSC survey, and we're using regions where it's complete. Okay, and the green regions have well-known surveys at Cosmos. Okay? And so this is, so we chose our redshifts. We chose redshift slices to match the 4,000 angstrom break between two wave bands, which I'm trying to show here. Okay? So our redshift slices are at, what you see in the next slide. Okay. Well, we don't see it, it'll be in the following slide. Okay. So here I'm showing color versus redshift for four adjacent bands, wave bands, right? So you can see what we're looking for is bimodality in color to separate the star forming in the bottom with the passive on the top. And you can see that there's a pretty good break here, there's a pretty good break here. There are hints of a break here, of a split here, bimodality, and here it's very iffy, but here we see with good eyes on the monitor, you see there's an excess on top. And in the thick red are our redshift slices, okay, where we think we are doing well. So if I keep going, this is color magnitude diagrams, color versus the redder magnitude, okay. Actually, you don't see this very well here at all. Okay, I'm disappointed. But on the screen, on my screen, we should zoom in, we see very well by modality, okay. And the black line, no, wait a minute. Yeah, so the black line is separated, okay. So I'm sorry we don't see it here. And we try to work in magnitude limited samples, okay, where we think we're complete. So, now to the results. So first I'm showing the fractions of red galaxies in the four redshift slices split for the satellites, which are the circles, by absolute magnitude, and also for the centrals, which are the stars here, okay. So let's start with the centrals. So the centrals, you can ask whether they are whether the fraction of red centrals is decreasing, which is not really the focus of this talk, but just to talk, it's just a side effect. And we see that the luminous centrals are not evolving much, and the less luminous centrals are evolving more. Okay, we only put a few magnitudes for the highest redshift. Now let's go on to the satellites. For the satellites, we do see decreasing red fractions as a function of R over RV for all redshifts, except that, you know, if you look carefully, at the highest luminosity, you don't see much of a decrease, okay, in the lowest redshift band, okay? But otherwise, it's pretty conspicuous, okay? Okay, we move on. So here are surface density plots with NFW fits here made up to 4 real radii for the red and the blue populations for the 4 redshift slices. And what you see is that, so the NFW plus constant field fits which is not a great model, by the way. So pundits will tell us you should use, Benedict Deemer would say that you should use something which is steeper than NFW towards the 1-2 virial radii, and that this 2 halo term should field the NFW halo, so it should increase. And that's maybe why we have this excess. But overall, it's reasonable. Okay? And there's one thing funny, which is that we have sometimes excesses of inner blue galaxies in the center, which if we read the web page of HSC, they say, be careful with the photometric redshift deep inside the clusters. Okay. So here are shown the NFW scale radii for the blue and the red populations, fitting up to 2 and 4 virial radii. And you will agree with me that the lines might be getting closer, but there's no reversal. Okay. However, if we go to only 1 virial radius, then there is a convergence at redshift 1.3. And this redshift extends to 1.42. So it depends on how far you go. Okay? And so we haven't finished our robustness test, but what we think is going on is that when we only stop at 1 virial radius, I think I mentioned this here, yes, if we stop at 1 virial radius, our likelihood is more affected by possible bad photometric redshifts deep inside. So what we have to do is that we have to simply make a test where we increase our minimum radius, okay? So let me move on. So here's some other robustness tests. Photos equality. But I'm not sure we did the best comparison here, so we have to play more with this. Our choice of the cluster center. So we took the closest BCG, we took the BCG, the most luminous galaxy within half the virial radius of the cluster. The virial radii we got by abundance matching. And so if we take instead the official center of the cluster, then it makes very little difference. So we're fitting here out to 2 virial radii. The satellite luminosity, we saw some trends before, okay. But here again, we didn't, it's preliminary because we didn't, I don't think, we did it by quantiles and not by absolute luminosity. And then we can ask, okay, suppose that the people who found local segregation, not all of them did, all right? Those who did, who studied the local density, there's a debate on whether they find reversal or not. But suppose they're right. It kind of makes sense that they find it and that we don't find it. Because, as I said, we're tracing different astrophysics. You could have local segregation if you have pairs interacting. And if these they are gas-rich pairs, as we expect them to be at high redshift, then the tidal effects during the interactions and the mergers will compress the molecular clouds, form stars. Okay? Whereas the radial effects, they will see it a little bit, but not too much, because there might be other mechanisms that are more important that are going the other way, like ramp pressure, central AGN, whatever. Okay? So, my last slide is that our conclusion so far is that, but it's still preliminary, is that there's no reversal of radial color segregation to redshift 1.3, so our point would be here. Okay? That the local segregation, if it is present, as I just said, is be caused by gas-rich merger interactions. But we have to do more robustness tests, the minimum radius, and also region. We have the Cosmos region. I'm not sure we'll have enough statistics, but we might see something about this inner increase of blue galaxies, which no one has seen at redshift 0. And then with SDSS spectrum. And then in the future is bright, as everybody says, okay? So we have DESI, which we haven't looked at. MOONS is going to be like SDSS at redshift 1.5, so it's going to be absolutely fantastic. We're going to be able to get very robust groups of galaxies, like we did with SDSS. We'll be able to do it with DESI and MOONS. And then Euclid, by going to the near infrared, it will enable us to go to redshift 2 with the J band, and to redshift 3 with the H band, assuming that it works. And so we haven't done the feasibility studies yet. Okay, so that's it. Thank you very much.
Question? Thank you for the nice talk. Just one question. Can this excess of the galaxies at the center of the clusters be due to cooling flows? For example, we know the Persons cluster that is.
I hadn't thought about that. That's a very interesting question and possibility. So I need to look at the SDSS data at low redshift. There are clusters at low redshift, and there's a Coma cluster, and Perseus has nice cooling flows. And so, yes, I need to look at this. Do you have a reference I should read?
I can think about it and send it to you.
Great.
Not on the top of my mind.
Thank you. I like that. Yes.
So thank you very much, Gary.
Well, since I'm the last speaker, thanks the organizers for this wonderful TNCG meeting.
And the chairs today, as well as the other days, thank you a lot. I enjoyed all your talks very much. I enjoyed sharing French and Icelandic delicacies with you yesterday. And the fact that we got a great, nice hole in the bad weather for that. It was great to see you. So now go home and do science, so you have something for us to present in the next meeting. And check your training and make sure that you get Travis.
Regardez, voir si ça correspond, parfois, même peut-être.